For some reason, it's still very quiet, but yeah, welcome to 61C's midterm review session conceptual. I have no idea where to look because I can see myself up there and it's a little weird. But yeah, welcome. It's going to be 1 to 4, and yeah, we're going to go through a lot of material. Just as a quick kind of side note, we do recognize that people might not be comfortable with asking questions out loud. So we have a Piazza post for that. You can post your questions on there. It's the first one on the pinned one. I believe it's post 900. So let me just get the link here. So feel free to post any questions there. We're going to try to not use the Zoom chat for questions, mostly because that means we have to go through and transcribe them later on. But if you have like, oh, I don't understand this, or can you repeat something or whatever, feel free to drop it in there. I would say I would DM Sonika. Let me actually make her a co-host so that way you can all see. Because my screen is going to be mirrored, and so I don't want, like, say if your DMs to show up, then it's going to show up for everyone, but she'll let me know which topics to review. So you can always field your questions through there. And same for in person. If you're not comfortable with something, you can always join the Zoom call and like just mute yourself or don't join the audio, and you can ask questions there too, or on Piazza. But yeah, are there any questions before we get started? I've also never mirrored my screen before, so we're gonna see how this goes. So the slides have been posted on Piazza. Let me see if, yeah, I don't think I can see that. Maybe I'll join the Zoom room on my phone as well. That might help. So that way I can see any questions that are there. But yeah, welcome. So I realize it says TBT time now, but yeah, it's 1 to 4. I'm Caroline. I'm a 4th year EECS MCV student, and I will be doing a lot of talking at you guys today. And then we have, if you weren't here earlier, we have our AI. So this is Aaron, Sid, Sonika, and then Christopher. And they'll be presenting at various points, and they'll also be kind of like strolling around. So if you have any questions, you can always flag them down, and they can answer or like run it up or something like that. But yeah. So midterm logistics. So the midterm is going to be happening next Thursday, 3/3 from 7 to 9 in PT time, unless you're otherwise approved for any other reasons. So the default is going to be assigned to be in person. And you can always request a remote option. So the logistics post is going to eventually be an 880. It hasn't been posted yet, but it will be released later today. And that's the final information, like how do you request a remote exam, who can request a remote exam. Kind of spoiler alert, if you're not comfortable with being in person, or like think that you would be more comfortable with online or whatever, you can always request that. And it'll be basically exam. It'll also tell you things like how many cheat sheets you can have, what kind of like midterm review material should you be looking for. And since you're all here, you did the first step, which is coming to review session. The content will be all lectures up to the first part of last Thursday, which technically covers transistors, but you'll notice that when we go through things later, we won't actually be covering transistors in this kind of section, because it's one of those topics where it's like it's not really traditionally covered on exams, and that's because it got introduced last semester like as a very light, hey, this is how transistors work, and then it was just never talked about ever again. It's kind of providing a background in a sense, and then this semester got expanded. But the reason that we don't really like to cover things on exam like that just got suddenly introduced is because we have like no practice material. There are no homework questions, no lab questions, nothing besides like maybe some amount of lecture on it, no past exam questions. So that is why we're not covering it here, and that's also why it won't really be on the exam. But I will say, like, it's still good to know. Yeah, and so overall it's going to be closed book and closed internet. You'll be able to get cheat sheets, how many and how, whether they can be typed, printed, or written. It'll be all in the logistics, and it will be proctored. So in person, you'll be in an in-person proctoring room, and you'll be assigned to a seat. If you're online, it's going to be remote proctoring. Cool. Are there any questions so far?
Yes, so you said the logistics will be posted on Piazza.
Let me see if I can launch the meeting directly. I cannot. Okay, great. We're gonna get started then. So we had a survey that kind of went out to see. Oh wait, I realized. Online, I'm not screen sharing. That was a fatal mistake. Here we go. Now you guys should be able to see everything. Okay. Sorry about that. I was speaking in here and then I realized, yeah, that's not actually happening. So you can see like the general breakdown. We're going to be covering some of the heavier topics. So towards the bottom, like call, functional units, SCS, a little bit more towards the beginning. And then we're going to jump into C and memory. So C and memory kind of like shot up a little bit last I checked. And then we're going to have a break, and then we're going to cover some of the light, quote unquote, lighter topics, which fewer people seem to have a problem with, but we are going to try and get to everything. Cool. Okay. There we go. So yeah, if you kind of see a general breakdown, this is how things will look. You can ignore the time because I realized I broke this down for a 2-hour midterm review, but it always winds up being 3 hours anyway. So yeah, so now that we can get started, some of you guys might have seen these slides before. I'm going to try to make them different, come from a different perspective. And that's if you attend my discussion section, you'll see the same slides for the most part. Some have changed. But yeah, we're going to start out first with call. So just as a kind of overview, call stands for a compilation, or which is done with a compiler, assembling, which is done with an assembler, linking, which is done with a linker, and loading, which is done with the loader and the operating system. And you can see, kind of see like there's a pretty easy parallel there. Kind of see how this all works out in this kind of flow chart here. So we start from something that actually isn't the compiler, it's the preprocessor. We're going to ignore that temporarily. So we go from compiler and then we feed that output into the assembler and then that output into the linker, and then that output eventually gets loaded into memory, which is what the loader does. But to actually be able to do that, we want to come in with a prepped file. So something that the compiler is expecting. So that's where the preprocessor comes in. So you'll notice that this preprocessor actually takes in C files or CPP if you're working with C++, or .h files, which are header files, and those are basically considered like the libraries of C. And so after going through the preprocessor, it takes care of some of the substituting things that we'll talk about in a second. And then it basically takes those, copy paste things into where your code actually is. So it substitutes it in. And then you wind up with this intermediate file or .i or .ii file. So if you're curious after this and you want to be like, I want to kind of see what that looks like, GCC, which is the GNU C compiler, which is what we've been using in lab so far in the project, actually has different flags that allow you to go through and like look at all of these different steps and really examine like what the code is doing. So if you're interested in that, and if we have time at the end, I'll actually go through those steps and show you guys what it looks like, but it's pretty cool. But so what is the C processor? Well, it handles pre-processing directives, and directives are just basically things that start with a pound sign or a hashtag symbol, and these are just instructions to the preprocessors to say, hey, at these kind of pound sign places, I want you to copy some stuff in. So these include things like define statements. You might have seen this in the project in your lab or just online somewhere. Define basically just makes a nickname for certain values, and we'll talk a little bit more about this later on. You'll see include statements, which for all of you guys have seen this at this point. They go at the very top of the file, and these are including .h files or header files. And so this is where like function definitions come into play. And it's like, I want to be able to use a certain set of values or a certain set of functions that I haven't defined. So I'm going to include them. And then the C preprocessor, after it does its work, basically takes how those functions are actually defined and then places it in your code where it is. So it'll expand your code to produce a lot more. Like it's going to get a lot bigger. And then you'll also have conditional statements. I don't think this is covered a lot in this class. It might have been glossed over for like 5 seconds in lecture, but basically we have our standard if else kind of statements that everyone's familiar with at this point. But there's also conditional statements in the preprocessor directives. So this includes things like pound sign if, pound sign end if, so you're ending the if statement, pound sign if def, and then a pound sign else, etc. And so what all of these kind of do is it alters the code itself. So how does that actually work? Well, because we don't have self-modifying code in real life, because that's bad news. Well, what this actually means is, okay, cool, I'm pinned. So what this actually does is it looks at your code, and if it's surrounded by, say, if something or if def, which is if something is defined, and then you'll put in basically the constant or whatever value happens after that. If something is defined or if a certain condition is met, this section of code will be executed. Otherwise, this other section of code will be executed. And so you might then wind up saying after the preprocessor directive, your code will look different from how you initially wrote it. Certain chunks might be missing. And that would be in the parts that like don't fall under the truth kind of statement. So it's, for example, if true, do part A, otherwise do part 2. And so if A is true, then well, in your kind of compilation, so the rest of call process, part B won't be compiled at all. It'll just be entirely ignored as if it's never there. And the point of this is just to make kind of code compilation more efficient, because sometimes, especially say at the system level, if you have some stuff, it's like, oh, well, if certain things in the system are set, I want to make sure that this runs, but not this. And we don't want to bother like compiling all of that all over again. So it just kind of omits it from your code entirely. Does that make sense? Any questions? I will take your stunned silence as okay. Yeah, so you don't have to like memorize exactly what each of these do or how to actually use them. It's just kind of the concept of what preprocessors do and what they have kind of control over. So these are all called macros. So macros include things like data or objects or kind of control flow things. It can also include functions. Like you'll sometimes see in fancy C code that like there's a define statement and then there's like a weird function that's happening in there, and it's pretty cool. You don't have to worry about actually doing it, but that's what all of these kind of fall under. And the output that you get, which is the actual important part. So if you take nothing away from this, take the output, and that's a pure C file, and that doesn't include anything that's preceded by a pound sign. And that's what we take and go into our compiler. So the compiler takes in the C or the pure C file and then converts it to some other assembly language. So also as a kind of heads up for anyone who joined later or online, these slides are posted on the most recent pinned post on Piazza. And so if you're worried about like writing stuff down, you'll have the slides to go back to. So I wouldn't worry too much about like writing down everything I'm saying. Yeah, so how does it actually do this? Well, this doesn't actually happen for high level languages. Instead, what something else called interpretation happens. And so these both of these things fall under this whole umbrella of translation, because we're turning code from one thing and turning it into another. So compilation, you'll hear like, oh yeah, I'm going to compile my code and then run it. That's actually slightly like inaccurate, because compilation only refers to the assembly portion, and you still need to do the other 3 steps before you can actually run things. But what people typically mean is like compilation just turns it into the assembly section. And what's important about that versus interpretation is not machine specific. So we talk a lot about like, oh, machine architecture or like 32-bit versus 64-bit system, RISC systems versus CISC systems. That's a tongue twister. But we talk a lot about that because a lot of this is really hardware specific. Interpreters are not. So if you notice, if you have Python code or Java code that you've quote unquote compiled and then you're running, you'll notice that if you send that to a friend because they're having trouble with a project and have them run it, they'll also be able to run it. Don't do that, because that'll get academic dishonesty flagged. But it's if you're kind of sending just code to anyone from maybe like a x86 system to one of those fancy new M1 Max to literally whatever else is out there, they'll all be able to run it. And that's because the interpreter is kind of packaged into the language itself. And what kind of is outputted is this thing called bytecode. It's not assembly language. Assembly language is only for compiled things, but the equivalent for like Python and stuff like that is the bytecode. So this is also when optimization happens. And the reason that optimization is actually able to happen is because compilation is architecture specific. It knows the ins and outs of your system and it's like, I know you really like this particular thing, so I'm going to optimize it for that. And I also know that maybe this loop doesn't actually ever run because you gave me like a faulty input or something. So I'm just going to entirely get rid of it and not even bother checking. And so like it does all of these little things at different levels to make sure that your code can run as efficiently as possible. That's also why we say like, it's very rare that people will actually go and write assembly unless they're working with architecture stuff. And that's also why it's always like the compiler will always write better assembly code than you ever will be, no matter how skilled you are. But that's not to discourage you from learning about it. That's also why we know that things like, for example, C and C++ run a lot faster than Python or Java do. And it's because we can optimize for the machine and we can optimize for all of these things that the interpreter doesn't know about. So this is also why this is a bottleneck. And what I mean by bottleneck is we don't want to compile more than we have to. So this comes into play a little bit later. So the output of the compiler will have all the standard assembly language things, which includes labels. So we'll see this in branches, in loops, in temporary labels, which you don't have to worry about, and then function labels, things like that, things that we as humans can read and say, huh, I can identify you later here, and it's really obvious to me. It'll also include pseudo instructions like move, like jump register, like jump, and it'll also include fully relative addressing. So we have two types of addressing that we've talked about up until this point during the RISC-V section. One of them is kind of absolute addressing. The other one is PC relative addressing. And we know with absolute addressing, it's theoretically going to take exactly where it is in memory. But at this point, even those kinds of instructions will have fully relative addressing. And the reason is because, well, we don't know where the code is going to go in memory. We don't even know what other code we might want to link with this eventually, because it's very rare that we're only going to run one C file. Like maybe we'll have helper files, maybe we have libraries. And so we don't actually know where all this is going to go. So right now, everything is relative because we've just arbitrarily said our file is the only thing in existence, and we don't care about the existence of other files at this point. So there was something I think that was mentioned on Piazza and in lectures like, well, if RISC-V is basically machine code, like on the homework, that's what it said. RISC-V is machine code. So why does the compilation process not really produce like pure machine code, so stuff that the machine code can run as an output? So any thoughts? Okay, well, the reason is because machine code requires for all address labels and pseudo instructions and all of these things that make it easy for us humans to look at the code. It requires for all of them to be fully resolved in AKA in binary and in things that the machine can understand. So the assembly file here generated isn't really pure assembly. So it's kind of like finicky in that sense where it's like, yeah, like compilation theoretically should generate machine code, but it doesn't actually because of all of these kind of output like other things basically. Does that make sense? Yeah. Oh, so compilation doesn't actually do any of that. So this is the output of the compilation process. And so it's the next step that actually takes care of some of those. Yeah. So the question was basically, does the compiler take care of like the labels, pseudo instructions, and addressing? And the answer is like, no, that's the output, and that's what we will have, and that's why it's not machine code, but the next step will take care of it. Yeah?
I have two quick questions. The first one is that compilation and interpretation are both basically like translating something. But for the interpretation part, we're gonna like translate it to something and say bytecode. But won't this thing also be at the end of the day compiled?
Not exactly. So
How does it run?
yeah, so the question was kind of like, well, won't the bytecode that's produced from interpretation eventually be outputted at some point as the or be compiled eventually? And like bytecode is basically like the quote unquote machine code of the interpreter land. And so the interpreter is packaged in the language. You don't have to worry about how it's done, but like if you have to, like when you do the installation of all the languages and things like that, like Python, you have to install it. It installs the interpreter, and the interpreter will then run the bytecode from the code that you've written in Python. And that's also why, like, for example, there's so many different, like if you have Python 2.7, Python 3, 3.6, 3.7, all of them require different kind of ways of doing it because we don't actually, it's not the same interpreter in that sense.
So our CPU doesn't run Python, but it runs C.
Yes.
Python, but it
Yeah, so the CPU, I guess it like runs the interpreter. It runs all the processes that need to be done, but this CPU and like this stuff doesn't actually directly or translate all of that. And the compiler, like it's different from the CPU. Like the CPU doesn't directly go and compile things. The CPU
Yeah,
just
no,
drives, yeah, all of the actions.
At the end, it's like the CPU is gonna execute the machine code.
Yeah. But it
the
doesn't do it for
Python.
interpretation. Yeah. I think there was a question back there. Yeah. Yeah, that's a great question. So first one was the output. It will still be human readable, and yeah. So GCC allows you to look into all of those steps. So it's really fun to look at that. And the reason that it has all the labels and pseudo instructions and stuff like that is because at this point we don't necessarily. The reason is because it's like this compiler does one step. So it looks at some stuff and it's like, what's the most optimized way I can do something? And then so the stuff that it generates is not necessarily meant to be like exactly for the machine to read, because it still has to go through a bunch more steps. And then so once you have, for example, move, the assembler will know, like the next step, it'll know that move splits into 2 instructions. But at this point, like it's not necessary to go through all the code again just to replace all the pseudo instructions, because we'll be going through it again anyways in the next step. Was there another hand somewhere? Okay, might have hallucinated it or might have answered the question. Okay, I'm gonna move on to the next part. So the assembler or assembly. I see that there are 2. Yeah, I don't know if I should click on it. I would say, okay, if you want to message, or maybe I actually don't know if it's public. It seems to be public. Yeah, okay, so I'm trying to repeat the questions. Yeah, remind me if I forget sometimes. Sorry about that. Okay, so now that we have the optimized RISC-V or assembly file, so another one is like x86. That's what you'll probably see if you go through the different steps. So it'll look slightly different from RISC-V. The next thing that kind of comes out of this is going to be an object file. And we'll talk more about the object file in maybe like in a few minutes because it has a specific structure. But this object file is eventually what's going to be kind of the keystone to our executable later on. So in 61C, we're always going to have 2 passes to guarantee complete replacement of all of these labels, pseudo instructions, and things like that. And that's called a 2-pass assembler. So unless otherwise specified, you can always assume that in 61C, we're doing a 2-pass assembler. And what a pass basically means is going from the top of your assembly file all the way to the bottom. That's 1 pass. So, and then you jump to the very top again, and then go through it all the way through, and that's a 2nd pass. And just real quick before we get into the rest of it, does anyone have any hunches as to why 2 passes are necessary? Yeah?
Okay. Is it like if you like have a jump instruction, but then you don't like really know where you're jumping to? So like, I guess like the first pass is knowing where every like all the labels are, and the second one like, you know, if you're jumping, then at least now you know where everything is.
Yeah, that's pretty much it. So the reason is because I guess we're using Python again because it's a really easy example, and I think everyone here has taken 61A or some version of that. But in Python, like when we're first starting out, a lot of the time, like we'll have this instinct to be like, oh, I'm gonna call some function, and then it's defined like literally physically later in the file, and then we try to run that, and then Python complains, being like, this function was not defined yet. How many of you have done that before? Yeah. Same. I've done that multiple times. And then it's like, oh gosh, now I have to restructure my entire code. But the reason that that's the case is because Python employs kind of a 1-pass system. So it looks through your code top to bottom and says, okay, well, I'm going to collect all of the function names and things that like you've defined. And then if you reference it later on, we're all good. But if you try to reference something that you haven't defined yet, that's when it yells at you. And that's why we don't do it here. 1-pass assemblers exist out there. It just becomes an agreement between like the coder or like the person who's writing the assembly and then their assembler that says, hey, I know that you don't like it when I use things before it's defined, so I'm not going to do that. It's kind of like the agreement that we have with Python to not do that. But the 2-pass assembler kind of gets rid of that problem because on the first pass through, we're specifically looking for labels. So what happens is, well, we go through and we see, okay, well, maybe we have a jump label, and then we look at some kind of reference that we don't know where it is right now, but there's some kind of reference key that we have. It's like, okay, have we seen this label before? If we haven't, then we have a question mark and it's going to be put in some other kind of table. And we know that we have to figure it out later on. And then it keeps going and says, oh, wait, cool, this label loop is defined. And so now it puts it in this first table and says, okay, loop was defined at, say, some relative address. And it keeps on going. Oh, wait, we have a jump loop again here. And so now it's able to replace that loop with whatever relative address that we had. And it just keeps going all the way through to the bottom. And then once we reach the bottom, that's the end of the first pass. But then we jump to the very top again. It's like, okay, we have now this list of things that have question marks next to them. And we don't know actually where they go or if they're even in the file or if they are from an external file or some library. And so it goes through the second pass and says, okay, cool, wait, I had this jump loop before and now it's defined. So now I can replace that and we can consider that to be resolved, or at least for now, because it's still relative. And it just goes through the entire kind of code again. And every time that it hits one of those things that it had a question mark next to it, it'll try to replace it. And if it can't, it'll stay a question mark. If it doesn't, if it can be replaced, then we consider it to be temporarily resolved. Does that make sense? Okay, I see general vague nods of assent. Yeah.
So in the first part, we store the labels with relative options.
We have stored relative basically, it depends on the assembler because there's a lot of assemblers out there, but generally it's stored the relative to the beginning of the assembly file. Because right now, all we really know is the fact that like we don't even have a program counter at this point because we haven't run anything. So instead, like the one constant that we do know is the fact that we have a top of the file, which we can maybe consider to be 0. And then we can keep on going down and then say, okay, well, this kind of thing is offset 8 instructions from the top. And so we know that to be relative to the top. And that's something we can guarantee. Does that make sense?
And the second part is it's a table.
Yeah. So basically the second pass says, okay, these question marks, questions that I had before, I don't know where they were defined. Can I resolve any of them? Cool. Okay. So we talked about tables and we have 2 tables that we get generated. What a surprise. So the first table that we have is the first table that we were talking about over here, the very real table that we have. And it's called the symbol table. So it's filled with labels and the relative addresses of where they're defined. And the relativeness is like some like assemblers might say, oh, relative to the bottom. Some might say relative to a certain offset from the top. If you're ever asked to solve a question like this or even some realm of this, you'll be told like basically where the offset is from, but you can just assume right now that it's from the top. And so the symbol table just literally fills it up with label 1, label 2, label 3. All of the things that have been defined go in the label table, and it's kind of the symbol table itself is labeled with like, oh, symbol table of say file A. And so later on, this also gets used during the linker stage, and we'll see in a bit. But it's basically used as a reference key for this particular file has these labels defined offset from, say, the beginning of the files at these positions. Does that make sense?
So like if you have the symbol table, right? So it will look at, so the symbol table will just be like the question mark labels, like the ones it doesn't know, or it'll just be every single label that the assembler knows?
It's the ones that were defined. So they're the ones that were defined in, say, file A, and those are the ones that you can definitively say, this is where it is in the file. So there's no question about it.
So like if you have like a built-in function that wasn't like defined in that file, like it's a built-in function, so that will not be in the symbol.
If it's a built-in function to what?
Like if you decide to like use a function that was defined in another file or like a library function, like will that not be the symbol table?
Yeah, exactly. So functions that are defined in libraries or in other files, so those are called external references. Those won't be defined in the symbol table because the symbol table is for that particular file. This is like my own reference key of things that exist in the current file we're looking at. Does that make sense? Okay. Yeah. Is the what?
The object file.
Oh, the object file, it is not, no. Yeah, it's the .o files that you might see occasionally, and if you try to click into them, it's just like a bunch of weird symbols. So not human readable at that point. Yeah.
Is it on both?
Is what?
Isn't it on both?
So this, okay, so the question was the symbol table, is it created on the first pass? And the reason that the symbol table can be created just on the first pass is because when we're going through the first time, we're only, the symbol table is populated with things that are defined, not the ones that are referenced. So those are two kind of separate concepts. Like you can say jump label, and that's a reference to a function. But if you have, say, label loop, colon, and then et cetera, that's a function definition. And that's what goes in the symbol table. So that's done on the first pass. And the second pass, the stuff that have question marks next to them will reference the symbol table, basically, for that. So after the first pass, it'll all be defined in the symbol table.
So what was the second pass?
The second pass goes through and looks at forward references. So that's like, for example, if you use label loop before it's actually defined. And then so once we go through the code a second time, it'll say, oh, I'm using a function that we know like hasn't been like, we didn't resolve it on the first time around. And then so now we look at the symbol table to see if we know where it is. Does that make sense? Cool. So then that begs the question, what's the second table? And the second table is the relocation table. And that's this table that was on this side that very much exists. And it's for code chunks or references that need to, and for what operations need to be done later in order to compute the value that's supposed to be there. So in other words, what needs to be relocated. So this is something that you'll see reference to like relocation, like, oh, this needs to be relocated. What it basically means is we need to figure out eventually in the final kind of executable where things will be. And so the relocation table, when we go through this and fill it out, it's all of the external references and the things that need to eventually be absolute addresses that we haven't yet figured out. So PC relative addresses don't need to be relocated because they're always like offset from the eventual PC. But the absolute addresses right now, because they're still relatively addressed, they go in the relocation table in order to figure out, okay, where is my final destination, basically. Yeah. Yeah, sure. I was thinking about writing on the board, and then I realized that people might be a little far. I guess I can try. Let me see. I don't know how to look online, though. That's also. Let's see. Let's see if people can actually see the whiteboard. Oh, the joys of hybrid, but also we like hybrid. I'm now looking at myself on my phone writing, and it feels a little bit weird. Real quick, sorry, I'm gonna double check with one of the people. What is the people like now? The problem is right now, I don't know like what the recording will look like, which is a bit unfortunate. I realized I should have made someone else host so I can see my own side of things. Yeah, I think I spotlighted myself, and that should work. Oh, I did I not? Oh no, I haven't been doing it this whole time. Okay, I'm sorry about that. Okay, I think this should work better. Hopefully. No. No, that's not what I wanted to do. Okay. I'm just gonna trust and hope that things work out in the recording. If it doesn't, I will just like physically, I will make a diagram to make it a little bit more visible. Okay, I can kind of see myself, so I'll just write it really, really large. So yeah, if we have something, for example, like let's say we have, oh gosh, I have, I think my backpack. Okay, so if we have, let's say our, do people see? Yeah. Okay. I'm just gonna write some dummy code. I think online can see. Let me know if you can't. From what I can see on my phone, it seems to be okay, but yeah, let me know. And then we say, okay, we want to jump to loop, and we don't want to return here. jump. And then we're going to say we have some amount of code here that we don't really want to execute. This is just dummy code that we don't care about. And we're actually better yet, let's use a branch. That makes more sense. Let's say like branch equal something that we've passed in as an argument to x0. If these two are equal, then we're going to branch to loop. And so then we have loop right here after some amount of space. So let's say there are like 8 instructions here. So loop, we're going to say, okay, well, branch not equal to some kind of counter 0 done. So blah, 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 we don't care. And then we're going to do jump. Can you see down here? Okay, we have jump loop. And then we're going to define done here as red. Because we don't care about calling convention right now, because we haven't officially talked about it in the review session. Okay, so yeah, if we go through this, we can see that there are a couple of functions being referenced and also defined. So in blue, we're going to go for the functions that were referenced, and then in red, we're going to, or if that's visible, we're going to go for the functions that were defined. So can someone just shout out, where's our first definition? Which one? That one or that one? Second one? Right. I think I said red was defined. I don't remember. But yeah, this is our first definition of loop. What's our second definition in here? Done, right here. And then our first reference to loop. So our first reference to loop is here, and then our other reference to a function is here. So yeah, right here we've identified all of this. So let's say we're the assembler and we're going to go through. So on the first half we go through, okay, look at this. We don't have anything that we really care about in this one that needs to be replaced. So we're going to move on. And then we see this one. We're like, okay, branch, blah, blah, blah. Oh, we see a loop. We check our symbol table. So far, we haven't actually put anything in our symbol table, but let's actually make a dummy symbol table. Or say file A. And we're going to define this as just 0 or 8 instructions down, blah, blah, blah. And then this chunk is going to be, let's say, 1 instruction. So right here we go through and we say, okay, yeah, we're trying to look through here, and our symbol table right now has nothing in it, so we can't actually replace that. So then it's going to go in our relocation table. So I'm going to say just RL table for file A, and that's going to go in here. So loop is going to be fallen here, and we're going to just say, I don't know what it is, because I don't know if it's an external function. I don't know if it's something that's going to be referenced later, and we don't really care about that right now. So then we continue and we go through our 8 instructions right here, which 8 instructions in RISC-V 32 or 32-bit system. How many bytes is that? 32, right. So 8 instructions is 32 bytes because each instruction is 4 bytes here. And so then that's where our loop is defined. So, okay, we have 32 bytes from here. We have 4 that's going here. So this loop is going to be defined at an offset of 36. Or rather, sorry, 40. Yeah, 1 down. This is going to be defined at 40, and that's going to actually go into our symbol table. So loop is going to fall in here, and it's going to be say start of plus 40. This is a really simplified form of like what symbol and relocation tables actually look like. There's a bunch of junk in there that like you don't really need to worry about. The system kind of handles it in the next part. But this is the important information. So now that we go through and we're like, okay, we've defined loop, and then we read through the rest of the instruction and we hit our done. So where does done go right now? Right. And do we, okay. And so done also gets a nice question mark because we don't know right now. That's a beautiful question mark. We don't know what's going on with that right now. So then we're going to continue on our merry way. 4 instructions, how many bytes is that? 16, right. So this is 16 bytes. And then we know that's going to be 16 byte offset. And then we have a 4 byte offset here because it's the next instruction. So 16 plus 40 and then plus 4 is going to be 60. So done is going to be an offset of 60. And so let me count this quickly. Okay, we have 16 bytes here, and then we have, no, sorry, 64, because I missed this one. Oh, wait, I realized I forgot this one. We forgot to identify this one. This was another reference. Oopsies. I entirely forgot about that instruction, that it existed. Yeah, we're not here right now. Done goes in there, but we haven't actually looked at it yet because we need to look at the previous line. So we have our loop reference right here. So where does this loop go right now? Relocation table.
Oh, no, actually, no.
Yeah, does it go into either of the tables? Right, so because right here we look at our symbol table first and we see that it's been defined already. Here it doesn't actually need to go in any of the tables, so we can effectively just say, okay, in the output, so in the object file, this is going to be replaced with whatever the heck this is going to, however that's going to be referenced. So let's just say start of plus 40. It's going to be written in a like not this way, but the general gist is like, okay, it's going to jump to the start of the file offset 40, and that's where we know that loop is going to be cut. You can see it doesn't go into either of the tables there. And then now we can move on to the next line. So I forgot, so this is plus 4 right here. That's going to give us 64 right here. So done is going to go, where does this done go now? Symbol table, yeah. I see nothing wrong with that. So yeah, this is going to go into the symbol table as well as done. And similarly, it's going to be some kind of whack form of some offset from wherever it's going to be. And so it's going to be, it's going to look like that now. Oh, wait, I realized I'm dumb. We wrote that earlier because that was that much. Why did I erase this? This came from here, and I entirely forgot about it. So this is our first pass. That's what's happened so far. Yeah? The reason is because it's a reference to the label loop. So what we do as the assemblers, we look in the symbol table first, see if it's defined. It was defined and it was the, like wherever it's chosen to start offsetting from plus 40, because that's how we defined it earlier, since it was 40 from the top of the first instruction. And so in the resulting object file, we can just replace the loop with kind of the relative addressing. Yeah. That's a great question. So the first one was also double checking online. I'm trying to project however loud I can because I didn't bring my microphone to home because it's at a friend's house right now. Can you still hear me okay? Yes, okay, lovely. So yeah, if it seems like I'm yelling, that's why. So the reason is because we know that we have so this was at position 0, this was at position 4, and we can see like one instruction later, it's a plus 4 offset because it's 4 bytes. And then we know like 8 instructions kind of happen right here. So starting, that's going to be a 32 bytes worth of offset, and then we have our next instruction right here. And oh wait, I realized that's actually going to be, it's going to be 36. Yes, okay. Yeah. So, because there's no extra instruction here. So 32 byte offset is all 8 instructions, and then that's where our next loop is going to be. This is actually going to be 36. Does that answer your question? Yeah. Okay. Yeah. Yeah, so the question mark is in the relocation table.
Why is it 56? Is it 22?
Yeah, so we can see like, okay, one instruction is here, and so the next instruction is at position 4 times however many instructions exist before that. So we have 1 instruction, 2 instructions, and then wait, why can't I do math? 1 instruction plus 2 instructions. That's okay. Sorry, 1 plus 1 is 2, and then we have 8 right here. That gives us 10. I'm so sorry about this. I cannot math anymore. So it's going to be 40. It's 40, and the reason is because. Oh, use a darker color. Green doesn't show up, I'm guessing. Okay. Does red show up? Okay. I wonder. Does this like? I wonder if we can like stack the chairs to make it higher or something. Yeah, so the reason is because so yeah, for online also I'll write in slides basically that kind of cover this, so that way you have a visual representation that isn't like some super low quality one here. I don't think that's gonna work very well. I'm just gonna hold it like that. So yeah, the reason that it's 40 is because basically the address is how many instructions have occurred before it times 4. And so I couldn't count apparently because I kind of forgot about this. So we have 1, 2, and then 8 instructions here. So that gives us 10 instructions that occur before the loop. So that means the offset here or the address here is going to be 40. So 4 times 10. So we use a dark color. I can't count and or do math apparently. And so yeah, to answer the question mark question, it's because I was going to do color coding, but I don't think that'll work very well now. So the reason is because every time we reference something, if we cannot replace it, then we just straight up like cross it out and then replace it with what's defined in the symbol table. But if we can't replace it, then it's going to go in the relocation table. And that's because right now we don't know where it's going to be, and we don't actually actively go through the relocation table until later. So right now, like all this is question mark. And yeah, after this, I will make slides basically that like cover what we have on the board right here, but in better quality and slightly neater. Does that answer your question? It's because at this point, this was referenced. So this loop is this loop right here. Oh, okay. Yeah, so at this point, it hasn't been defined yet when we went through it the first time. It doesn't automatically update because that's what the second pass is for. Yeah. Sorry.
Just to confirm, are there any blanks on the symbol table after the first pass?
Symbol table, no. So symbol table will never really have any question marks because those are just like kind of filling things in as they're defined.
And the second question was just what is SA soon?
Oh, file A. It was just a way of like referencing file A. For if you have more files later, yeah. Cool. Okay. So, okay. Well, we're gonna go through a second pass, and then we're gonna move on just in the interest of time. But yeah, for the second kind of pass, what we do is like we go through and we say, okay, first line, nothing's there. Second line, okay, well, we already know that loop was sort of referenced in the kind of relocation table. So now we look at this relocation table entry. Okay, loop, you have a question mark. We look in the symbol table to see if it could be defined. It is defined right here, so we can now replace this with this value right here. I'm not going to write it just because too many words up here. But now that can be replaced, and so this will no longer be a question mark, and it's considered to be resolved. And we keep going through the entire file in this similar way. And so then the next one that we see is done here, and we see that it's been defined as well. So now we can replace it with this value, and this has now been resolved. So if we, for example, in here had some like J or JAL RA, let's use malloc because that happens in project 2. So if we have like JAL RA malloc, we can see that that hasn't been defined in the symbol table. It would have gone in here, so malloc, and that would have had a question mark. And on the second pass, that still will have a question mark because it hasn't been defined in the symbol table, so we can't replace this. So this will be considered an external reference. And so that will stay in the relocation table for the next stage. Does that make slightly more sense now? Yeah.
So like the relocation table doesn't like remove the relocation table, just fill in whatever like on the second pass, like if it's if it already found in like an address for that, it'll just replace the question mark with address.
Yeah, so it replaces it in the relocation table. So like all of this, like question marks and stuff like that, crossing out, it's just for it kind of visually. How it's actually done is like really complicated about like what bits like are set and stuff like that. So you don't have to worry about like the technicalities of it. You just think about it like, oh, it will be eventually replaced in the code, and then the relocation table now has a value instead of a question mark.
And one more, like, what if the label is defined before you like reference it? Like, is it possible for like a label to be defined?
Yeah, let's say we have something like start of A, and then we have some code right here, maybe a couple of lines right here. That's totally possible. So like you can have start of A, maybe let's call it loop because this is some bigger loop in the grand scheme of things. And so loop start of A, it'll have gone into symbol file, symbol table for file A, and maybe like at this point, like we'll want to like jump all the way back to the top if there's some branch condition. So it's totally possible for labels to be defined before. And also just as a good coding kind of convention, you'll notice like in project 2, if you've looked at it, I hope everyone has looked at it to some extent, since it was technically due on Wednesday, but you'll notice at the top of all of your files, like there's like a label. It's like a relu or a matmul or something like that. And that's still a label, even though we don't call it from inside our function. So that's still going to go in the file table, or sorry, symbol table. Does that make sense?
So when I guess like reference, then you still write something in the relocation table, but you do not put a question mark because it's already been, defined.
Wait, sorry, could you repeat that first part?
Yeah, so like if a label has already been defined, right, and you put a symbol table and you have an address with it, so if you do decide to reference it after you define it, you still put it in the relocation table, but
You won't.
rather than a question mark, you put the.
It won't go. It won't go in the relocation.
Oh, it just won't go.
Yeah, because relocation only happens when something hasn't been defined at some point. Yeah. So yeah, if you have any other questions about assembly or assembler or anything like that, feel free to flag down one of the AIs because we do need to move on for the interest of time. Okay, so 2 passes, are they always necessary? What if there are no forward references? I'm just going to go over this because it's interesting and it's a good thought question. But if you're using a 2-pass assembler, it'll always guarantee 2 passes, even if you have no forward references. So if your code is like, you can technically go through 1 pass and be okay because the assembler itself doesn't know that it has no forward references. So it still needs to do it to guarantee things. Cool. Okay. So now we're going to go into the linker and linking. I'm going to go through this a little bit quicker just because time. But if you're confused about anything, just the AIs can answer your questions. So yeah. So what happens during the linker and linking is it's going to basically sum up all the object files. So the star stands for just like whatever random name that you have, and it's going to output some executable. So O stands for object file, and we're going to take a quick look at what the object file actually looks like before we get into get too far. So our object file starts with an object file header, and so this is pretty standard for like most like things that need to be mapped. So if you eventually take like the web class or maybe 161, you'll hear about like, oh, internet protocol headers, stuff like that. There's a lot of these things like HTTP headers. But what this includes is the size and position of later components. So what other later components are there? Well, the first one is the text segment, and that includes like the actual machine code, which has, because it's machine code, it has resolved all labels, all pseudo instructions, and it has the absolute addresses filled in at that point. And we'll see how that's done in a second. It'll also include the data segment, which is a binary form of all static data. So this might be globals, this might be constants, stuff like that. And you'll notice by the name, but the text and data segments refer also like the names are the same as the text and data segments of memory. And that's kind of a hint later to like, oh, where certain things are loaded eventually in memory to execute. And the object file actually also includes the relocation table. It includes the symbol table, and it includes debugging information. For example, if you use BDB, it needs to have the debugging information available. So the question here is like, well, at this point, why do we need the relocation table and symbol table? And the reason is because A, relocation table still needs to have stuff filled in. So for example, here, malloc, we still don't know where it's defined. So the linker is going to take care of that, but it needs to have a reference of what hasn't been defined yet to be able to do that. And the symbol table, why do we need that? And the reason that we need that is because we still need our reference key for other files to look at, sorry. So at this stage, we can see that all of the different object files that you've generated or are going to link together, they're now going to like cross-reference each other's symbol tables, and that's what the linker takes care of. Because, like, for example, malloc might be defined, say, in file B. but we don't have access to file B symbol table until the linking stage, because that's when all the files start looking at each other's stuff. Oh, I took my snap. So going back to the linking stage, it first categorizes different code chunks, which are called segments, from each object file that was outputted from the assembly portion, and then groups them together in order. And the order here, it actually is not predetermined because the linker itself is defined. And that's why, like, from the assembler onwards, basically, it's very fuzzy in terms of like, oh, what exactly happens? And it's fuzzy because we don't actually know. And that's because assemblers, linkers, loaders, they're all like, they can be written in a lot of different ways. And there's like no real standard to any of this. So for example, like if we have 3 files like A, B, C, it might be ordered B, A, C, C, B, A. Like just depends on the linker eventually. But what we do know is that the text and data segments, the order is going to correspond to each other. So if in the data segments ordered like C, A, B, like from top to bottom, then in the data segment, it's also going to be C, A, B. The standard text segments or segments that we have are the text and data. I can't really think of a reason that we would have more than that. I'm not aware of stuff that will have more than that. And this is also the stage that all references are resolved. So all absolute addresses will now become absolute addresses, and they will no longer be this kind of wonky, well, it's an offset from some other thing. So it references from the user files, which takes a look at all the different symbol tables on file A through file N, however many you're doing. And then it looks at all the external references that you have, which basically are coming from library files. So there are 2 ways that you can link the library files. The first one is static linking, and this is basically just taking the current library files and then smushing them all in with your data with your files at that one point. So if you remember from earlier, like the diagram, let me see, pull it up. Oh, no. Hello? There we go. So if you see, if you can see this diagram here, we see at the linking stage, we have a static library that has an arrow pointing in towards it. And so that kind of references how it's actually being done. So eventually in the executable with static linking, all the libraries that you'll be using, including all the functions that you won't use, are now in one giant executable. And so it'll be a really, really large file because of that. So some pros to it are, well, if you need to reference it, you have it all in your executable. You don't have to look anywhere else. So it makes it really fast to reference. But the downsides are you create a really large executable because everything is there, including functions that you don't need. And it also means that whenever, say, if you need to update one of your library files, then you have to go through this entire process again and go on regenerate everything and regenerate the executable. And it just becomes a very labor intensive process. So there are reasons for wanting it and also not wanting it. The other version that we have is dynamic linking. And so dynamic is the opposite of that. So if you've ever looked in the home bin directory, so binary directory of, say, WSL or your Macs or whatever, you might notice, like if you've gone on an adventure in there, that like you have like a C folder, a Python folder, a Python 3.6, a Python 2.7, all the different versions of Python in there. They have their own folders. And if you click into them, like in the C folder, there will be a lot of .h files. And that's what dynamic linking and static linking are kind of referencing. So static linking will take the header files and shove them all into the final executable, but dynamic linking will kind of go to that kind of directory and look for it every single time. And so you can see that like, oh, when it actually runs, it'll be a little slower, but it also means it'll have the most up-to-date versions of the files. So it's positive in that sense. And then it goes through all relocation entries. And as a result, all absolute addresses are filled in because now we know, oh, malloc was defined in file B with an offset of like, say, plus 56 from the top of file B. And we know that file B in like the CAB file format comes after C, it comes after A. So we know after A, it's going to be a offset of 56. And so eventually can do all the math to figure out in this giant code chunk, where is it going? So that begs the question then, how does the linker know what absolute addresses are if we haven't specified a place in memory to load to? Because remember, the absolute addresses are actually all in memory itself. And right now we haven't loaded them to memory. So like technically we're looking at it, it's like, okay, it's the chunk of C plus the chunk of A plus the offset of like 56 here. That's still technically relative. So the reason is because of that issue, we need to actually have some sort of absolute address at this point. And so it decides, the system just decides, okay, we're going to start like loading our code eventually at this one position. So here it's going to be 0, 1, 0, 0, and then all zeros at that position in memory. So it's pretty low. But there's still a lot of stuff up there. So it's going to load it there. And so it's going to say, okay, the code segment comes first, and it's going to be this size. And so things that I'm going to be referencing will start from this base position. So that's how it kind of eventually calculates all of that. Are there any questions? Yeah.
Just a quick one for the order. Can you just clarify what you mean by sometimes you cannot define the order, but sometimes?
Do you mean under like the second big bullet point?
Yeah, it's something like.
Oh yeah, so the linker, it's the order that like the files are ordered in, so like the different chunks are ordered in are defined by the linker. So because we don't have like a standard linker that we're really staring at right now, we don't know like if it'll be ABC, ACB, etc. So that's why I'm saying like you don't have to really worry about like what's the exact behavior of the linker. Yeah. Yeah, once it decides on the order, then all of the different segments are going to be ordered like that. Okay, if you have any other linker questions, feel free to either ask on Piazza, flag down one of the AIs, because we're going to be moving on. Sorry, I would answer more questions, but yeah, time. Okay, the last step is the loader, which does the loading portion, and this is the part that it's going to be like most high level understanding our explanation. So you don't have to worry like how exactly does this work. And so what happens here is you take the executable that was just created, and then it's going to wind up in memory somehow. So what happens is the loader is actually really closely tied to the operating system. And that's also a reason why like we don't teach like exactly what goes on in that, because like OS comes like a little bit later. And also there's an OS specific course that spends an entire semester teaching about all of this. But just generally, it sets up the space needed to load all of this, because we need to know like, certain areas of memory we shouldn't be able to write to, certain ones we should only read from, certain things we should execute. And so we don't actually want to we want to know the permissions and to be able to set the correct permissions for certain addresses in memory. So that takes care of that. It also initializes the stack to hold whatever arguments you pass into the executable. So if you say like, I'm executing, I don't know, snake, and then you have like say 4 arguments, then it wants to be able to set up the stack to read those arguments correctly. It initializes the register, so it clears anything that needs to be cleared, for example, X0, and then, or it needs to set up, for example, the stack pointer register, so it takes care of all of that. And then the stack register or the SP register is then set to the stack pointer address, which is going to be all of the setup and then the first available address after that. And then we have additional routines. So you can say this is very, very high level. I would just say like if you have a general understanding of like what's going on, that's totally sufficient for the breadth of this class. But if you're curious more about it, we can chat about it after the review session, or you can spend a semester taking 162. Cool beans. Are there any general questions for this? Okay. Cool. Same one. I thought I got rid of that, but apparently I didn't. So really quickly before we move on, just the executable kind of order. So executables have an executable header, and that includes the size and text of size of text and data segments. Like we don't need to know at this point where they are going to be because we've already defined it. And the text and data segments themselves are going to be there. So we can see that there's a pretty strong parallel to the object and executable files. They both have a header, they both have a text, and then they both have a data segment. And then the rest is not really needed. And so that's why we have one kind of file format for both of these. It's called the ELF, or the executable and linkable format. And it's just because it's really easy to interpret one file like format for 2 things instead of having 2 separate ones. Okay, cool. How are we feeling? Do we want a bit of a break? Do we want to jump into timing SCS before we hit the break? Break? Okay. We have this room until 5, so technically if we go over, we can still keep the room. So let's meet back at 25. Yeah? Online, feel free to go take a bathroom break or get some snacks or whatever. And yeah, as always, if you have questions now, you can always come and ask them now as well. Okay, cool. We're gonna start again. Yeah, it's 2:25, so we're gonna move on. So we're gonna depart from the land of call, which we can all collectively heave a sigh of relief. And then move on to a more exciting topic. not the practice questions. We're going to skip that. SDS. Whoa, who's excited for this? So SDS stands for Synchronous Digital System. That's how you might have seen it written out. And this includes like the Boolean logic part, the timing portions. I also realized, oh, I look very weird on camera right now. But yeah, so I do have to say, I wasn't sure like what style the slides are going to be for this section. So certain parts are going to be a little bit more in depth than others. But we'll go back and add some more slides. Just basically like if we write anything on the board, we'll kind of transfer it to slides after this, just because it's not very clear sometimes. So let's review some definitions. SDS is one of those topics I didn't personally understand until I started teaching summer 20. And I was like, oh gosh, this is how it works. That would have been useful to know 2 semesters ago. So if you're feeling confused about it, totally normal. So let's go through some definitions. So the first one, and one of the most important ones, is the clock, usually abbreviated CLK. And this is the central timing unit for any kind of synchronous digital system, any kind of like time system. And it's usually we only have 1 clock per system. And this is because all of the timed units, so the units, the objects with like the little arrow triangle at the bottom corner or like bottom of it, that represents a time unit. And all of those things usually behave under 1 clock cycle or 1 clock. Anyone have thoughts as to why we don't have like clocks, like 5 different clocks out there with 5 different timings? Yeah, exactly. So you get out of sync things. So imagine if you like your arm had like 1 heartbeat and then your leg had another one and then your chest had another one. It's kind of like, well, I don't know what's going on and I'll probably die. So same with the SDS, like it just doesn't like that because we don't know when values are going to be updated. We don't know what to obey. That being said, like a really large system, for example, might be able to like get away with 2 clock cycles if they're properly calibrated, if certain parts need to run at a faster speed than other or can be more efficient, but you don't have to worry about that for this. That doesn't mean though, all timed units will be following the same clock signal. So you might have seen this on discussion if you went to discussion. If you haven't yet and you want more practice, Monday there's a 1 to 3 discussion on SDS, but what this basically means is sometimes the clock cycle might be offset, or it might have gone through like an inverter or something like that. An inverter is just a not symbol because it reverses whatever signal you put through it. And the reason for that is because you might want to manipulate the clock cycle, but that doesn't change like the period, so the frequency at which it goes. It just changes like, oh, at some parts, like some things might be looking at a 1 signal, some might be looking at a 0 at the same time, but it'll still be like going up and down in the same kind of order. Make sense? Okay. A state element. So this is any clocked element, aka any piece of hardware that follows the clock. So there's some elements, like for example, the Boolean or the functional units, like the AND gates, NOR gates, etc. All of the gates, basically, those don't follow a clock, and we'll talk about that in a second. But things like registers, flip-flops, memory, for example, they'll all follow state elements, mostly because they hold certain values. So that's the difference between the two. State elements has persistence, aka it stores things, whereas logic elements or non-state elements are unclocked. They don't obey the clock, and it has no persistence. So basically, once a value passes through it, it no longer remembers it. All it does is like, oh, it might and things, it might like flip the signal, but it has no recollection of what goes through it. Yeah. Yeah, basically. Whereas clocked elements kind of like, they don't constantly read it. They only read it on obeying certain rules. And logic elements are also called combinatorial logic elements. So we'll see this abbreviated as CL later on. Flip-flops, abbreviated FF. So these are state elements that store 1 bit's worth of values. And they like look like registers as well, like on diagrams. It's just that they happen to just store 1 bit instead of 32 bits, for example, or 64 bits. And a register is an n-bit state element. So registers in this class, we are using 32-bit registers, at least for the foreseeable future. And it's usually created with n-chained flip-flops. So what this basically means is like, if I'm trying to feed a 32-bit value into something, I'll have 32 flip-flops, 1-bit flip-flops, and each of these is going to store a single bit. So like when you're writing a binary value, like you have 001, 001, or whatever, those 0, 0, 1, they get stored in individual flip-flops. Does that make sense? No, that's EE, the whole EE thing. So that's also like transistors. Transistors are basically what like flip-flops are typically made out of, what a lot of these elements are. And like the reason like we don't super cover them and we've never really covered them in the past is because knowing that they exist and sort of what they do is fine. But like, for example, doping like semiconductors and stuff like that to make them actually function in certain ways, that's in EE land. That's stuff that we don't touch. Yeah, okay. So the definitions are on the slides, which are linked on Piazza. So if you haven't gotten it all written down, that's okay. So up here we see a pretty standard clock cycle. So like it goes from low to high to low in a pretty regular pattern. So the next kind of thing is the rising clock edge, or RCE. This is a period of time. It's usually considered instantaneous. We can see all of this is considered pretty much instantaneous because like we see the right angle. In real life, it's more of a little slope, but like it's negligible. Real life happens at some points. And so this is when the clock goes from 0 to 1. So for example, our first rising clock edge is where that little thing is circled right there. Our falling clock edge is kind of the opposite direction. So it's when the clock goes from 1 to 0. And that is on the purple section. So the second one that just showed up right now. So in 61C, timed units are usually following the rising clock edge. In some classes, in some kind of units, they'll obey the falling clock edge. And I don't think this was actually talked about in lecture, but it's something important to note is like, we know that registers are written to on the rising clock, or sorry, yeah, are written to on the rising clock edge, and like one action happens per register on the rising clock edge. But you'll see this on past exams where it's like, oh, assume like in a single clock cycle that 2 register operations can happen. So for example, a read and a read, or a read and a write, or a write and a read, and stuff like that. And the reason that that can happen is because those particular actions are also timed on the falling clock edge. That won't really matter until we start really covering data path stuff, so you don't have to worry about it for the midterm, but just something to keep in mind that falling clock edge is useful. Yeah?
So you're saying one clock cycle is rise, against the pattern is something.
Yeah. Yeah, so one clock cycle is from rising to rising. Okay, so the setup time is the amount of time before the rising clock edge for which the input must stay stable. Okay, like this is just a particular rule that we have. It's not, for example, something that's like, oh, you have to determine like how long the rising clock edge should be in like actual logic, but rather this is set by the actual system itself. And so it'll look something like this, for example, like this is just some arbitrary amount of time. This is defined by the hardware. The hold time is the same as setup, but for after the rising clock edge. So it looks something like this, maybe. So basically the amount of time that an input must stay stable after the rising clock edge. So by that, we can also say between like the first dotted line and the second dotted line, the input, so to whatever thing that we're timing right now, must stay either high or low, and it can't change in between that. So it can't like drop down or something like that. And then the clock to Q time is the amount of time after the rising clock edge it takes for the input, so the D side, to be realized or accessible on the output Q side. So that's why it's clock to Q, because after the rising clock edge to when it shows up on the Q side, that's the amount of time that we need. And so this is also only after the clock to Q time can you sample the value from the Q side correctly. So if you try to do it before then, you try to read from the output, you'll get a value. It just might not be the value that you want, and we consider that just to be garbage again. So even if it's correct, still wrong. So clock to Q time is either greater than or equal to the hold time. So clock to Q, maybe something like that. So we can see that these will be reflected on all of the other cycles. So we can see that the setup time is kind of during the quote unquote same clock cycle as like that one, the first one that we're looking at, but the pattern repeats itself onwards. So we're going to look at a possible, like a pretend sample input. So right here, do we see anything wrong with this input? And I say it like that, there might not be anything wrong with that, by the way. So, yeah.
What do you mean by wrong?
Or as in, does it violate any of the timing conventions that we have? So we know that the setup time has to be held, the hold time has to be held for it to be correct. Yeah.
It's just like a rising, right? From the coding.
I'm not 100% sure what you mean by that. Like with respect to the falling clock edge, it's
I guess if you read the input on the phone, on the input change. Oh no.
oh, do you mean like between the hold and clock to queue time it changes? I wish I had a pointer. I should get a pointer.
I missed that.
Okay, no worries. Yeah, wait. Where did it change before the hold time? Do you mean like here? Yeah, so we see that it goes from 0 to 1. So for online, it goes from 0 to 1 right here. And oh, you can see my mouse. Cool. Excellent. I forgot about that. Yeah, so it goes from 0 to 1 right here. And that looks a little sketchy, but good for you for pointing that out because that is actually okay. And the reason is because it satisfies the setup time, it satisfies the hold time requirement, and then it changes between hold and clock to queue, and that's okay. The dash line. Oh my gosh, why am I trying to go over there again? This is the clock to queue. This is the hold time. Yeah. So to clarify, yeah, this thing like this looks wrong, but it's actually okay. And the reason is because between here and here, it kind of all stays to be 0 or the low signal, and that's okay. And then after we kind of change over here, if we try to read this particular signal after the clock to queue, we'll read a low signal. And the reason for that is because that's what was written to the register in this time. Yeah.
What do you mean by like? How do you know what it works like? How are you reading it from those lines or like?
Yeah, so that's a great question. So when we have this, we want to make sure the setup and hold time constraints aren't violated. So if we look at this, we know like, okay, between this set of line and then this pink, like the rising clock edge, it has to remain constant. So we see that it remains at a low value, so that's satisfied. Same with between rising clock edge and then this dotted line right here, nothing changes in between here. So we can see our two timing constraints are held, and that changes between hold and clock to queue, but we don't have any rule that says it can't do that. So when we try to read from the register after that, it's still going to read as a low signal, and the reason is because between the setup and hold times, that was what was written to the register. Yeah. Greater than or equal to. The reason is because so there can be like the requirement, for example, like hold time could just be like really, really long. But the reason is because the setup plus hold time is basically the amount of time that's needed for the output to be read. And so because that's the amount of time it takes for the register to have all of its bits properly set, because like remember it's an n-bit chain set of flip-flops. So it needs time for like all those flip-flops to be set correctly. And that happens during setup and hold time. So that's why like the input has to remain constant. But after the hold time, then like we can start reading and they'll be correct. But if we say clock to queue is less than that, yeah, so we can't guarantee any correctness then. Okay, cool if we move on. Okay, so moving on just implies that we have another set of inputs. So we look at this, okay. Is anything violated? So in the kind of chunk that just appeared right here, is anything violated? Oh, I thought I saw a hand. Yeah?
Yeah, like in the one, like the third, like rising clock edge, the like in the area between the rising clock edge and the setup time, it changes, so it's not really changed.
Yeah. So that's exactly correct. So this violates our setup time restraint. So yeah, so this input signal goes from low to high during that amount of time. So that the reason that it is considered to be violated is because like we know it needs to remain constant to be able to write to the register. So if it suddenly changes, then like maybe half our flip-flops were written as one thing and then half our flip-flops were written as another, and it'll cause instability. And that just means that like that winds up being wrong. And then our last one right here, so we can see that like right here, it's like sits exactly at the setup time. And I just showed this example to show that basically you won't see things like this because it's really ambiguous, because in real life, like because we know it's a slope, it's really hard to tell So you won't see stuff like that because this should be okay, but like we don't exactly know. Okay, cool. Are there any questions? Yes, so we're gonna get to that in approximately 2 seconds. Yeah, so like these are all kind of like animated, they're transitions. So if you look at the slides themselves, like you'll see everything all at once. So yeah, so that's exactly what we were talking about. It's marked as like slashed out because basically if we look at things before our first rising clock edge, we don't really know like what the value is going to be read as. So this is just marked as slash out because we're like, okay, this is before we care about stuff, so we don't know. It could be low, it could be high, we don't care. So yeah, that's how I don't care is being marked as in signal. Okay, I'm gonna move on for the sake of time. So critical path is the longest delay between two state elements. So if we look at this, sorry, yeah, there we go. So if we take a look at this, we have two what appear to be registers. So one on the left and one on the right. So critical path is basically saying, okay, we have two registers right here. I'm going to calculate some amount of time between those two, but we might have multiple types of combinatorial logic paths between it, and we want to find the maximum. So the critical path winds up being the clock to queue of the first register plus the longest combinatorial delay plus the setup time of the second register. So this comes from register 1, and then for the combinatorial logic, it's the maximum of the sum of all in series combinatorial logic delays. So what that means is, for example, if we have like two operations kind of happening at the same time, that's not in series, so we don't really care about that because they operate in parallel. But if it's in series, we have to wait for like say gate A to finish before we can do gate B, and so that's considered to be in series, and so those are added together. And the setup time comes from register 2. And the reason for that is because the clock to queue time, it's basically we're looking from rising edge to kind of rising edge. So the rising edge like amount of time after that is like the clock to queue time, which is when we can guarantee that register 1 outputs the correct value to go into the combinatorial logic. And so then we take the maximum time, we meander through here, and then we want to make sure that whatever output comes from that stays stable during the the setup time of the second register. So that's why these two are included, but not the whole time and not more than once. Does that make sense? Yeah. Exactly, yeah. And also hold time is just something that we're like, oh, it needs to stay constant, but because we already know that clock to queue is greater than or equal to, and that's what we care about to see the output to go into the pink section. Yeah.
Sometimes like the amount of time it takes for the register to like see the input.
Basically, yeah. So it's we want to make sure because we're looking from rising edge to rising edge because that's one clock period. So we want to make sure all of the delays during that are counted. Okay, so then moving on to the next portion. So the minimum clock period, usually in nanoseconds, is equal to the critical path. And so this is basically what it's saying is this is the fastest that our system can go because the so the faster a clock kind of goes, the more efficient your system is, the more computation you can do. So we're always trying to maximize how fast our clock can go. But if our clock goes really, really fast, it means that the clock period is going to be really, really small. But we're bound by the fact that certain like constraints need to be had. So for example, if we have a really long combinatorial logic section and our critical path is super long, then we want to make sure that like it's given its proper time to do everything before we actually move on to the next clock cycle. So that's why it's bound by that. And then there we go. Our maximum clock frequency, it's in hertz. If it's nanoseconds, it's going to be gigahertz, is equal to 1 divided by the minimum clock period or 1 divided by the critical path. So these are all pretty standard calculations that you might see on an exam. Done it in homework 5 if you're confused about how to do it. I know there were a lot of office hours questions about that. Would definitely recommend dropping into office hours at some point in the next week or discussion to get those questions answered because these are very common questions on exams. Okay, so this is the last 2 things that we're really going to talk about when it comes to SDS stuff. I think I'm going to I'm gonna try to skim over this a little quickly. If you have more questions about it, I'm gonna answer them when the next kind of set of topics are going to happen, just in the interest of time. But yeah, these are two common questions that or equations that you'll have seen on the homework. So the first one is determining what the maximum hold time can be, and the other one is determining what the kind of clock cycle should be. So for this one, the reason that the hold time is less than or equal to the shortest path is just because, well, okay, if the value changes before it's actually written, that's going to be really bad. We know that like before the rising clock edge, value changing is bad as well, but that's before the like new clock cycle, so we don't really consider that. So instead we look at the hold time and we say, okay, well, if we know that the clock to queue time is going to be eventually winds up being like less than say the hold time, then things might change before then because a new input will be gotten, and so that would be really, really bad. So if we have a shortest path that's less than the hold time, it means that the value has the potential to change. Basically, if you have a really short path, you can come back. If the hold time is not viable, then you're writing something and things might change while you're writing it, and so it can cause all sorts of kind of confusion. And so the shortest path is defined as the clock to queue time plus the shortest combinatorial logic circuit. And then for this other one, it's similarly, it's what we talked about in the previous slide, but the clock cycle is the same, but with the hold time, and then the clock to queue time is greater than or equal to the hold time.
The shortest path is different than
Yeah, so the shortest combinatorial logic path is like, it's just the opposite. Like for the other one, we're trying to look for the longest one possible. This one's the shortest one possible. So we make sure that the hold time is less than that because we don't want the value changing before our hold time is over. Sorry. Back.
Are they all always relative? Like, are they, will they say like, oh, between the shortest path to register, or like, will they say like point A to point B?
So you'll have to find that. So there will be multiple, like sometimes in more complex circuits, there'll be like maybe 3 registers or 4. And you'll have to basically pick out which ones, like between which 2 registers is the shortest one, because all the register paths are timed by the same clock. So we want to make sure the shortest one is the one that's looked at, basically.
Yeah, and then you know, you did the starting input, it always like input output.
Yeah, so input to output, there sometimes might be like, for example, registers in between there. So you'll have to look at each of like the sub paths as well. Yeah.
Can we assume that all questions are going to be in nanoseconds? For the, you know?
They'll give you the units.
So like if you find the shortest path, like the shortest path, like to get the like the what is it, the longest hold time, then like is the clock to queue you use, is it for that register, like the register you're finding the longest hold time for, or is it like
So
which register are you using the clock to queue?
So we don't care because clock to queue setup and hold time are constant for all time units across everything, basically. Almost always. And the reason is because like Unity, unless you're like using a bunch of like different hardware. So like for the purpose of 61C, like it's all hardware are using the same 3 values, unless for some reason they specify elsewise. So yeah. Yeah.
Let's say something that we don't care about, we don't want.
So, okay, the question was if it's in a section of the circuit that we don't care about or want it to recompute, then why do we care about it? And I guess it's just because you can't really control, like, it's built into the hardware, like however it's being designed, like values will always reach a certain portion. And if it's in the logic, like in the hardware, then you'll want to use it at some point. So if you don't have, like, if you don't want it, then you do want to get rid of it. I think if I'm interpreting your question correctly. You mean like intermediate values? So yeah, intermediate values, they still count because even if they are not the final output, they'll still influence other values later down the line. So you want to make sure those are still consistent as well. Yeah. If you have any other questions about SCS, I will answer them separately, but we're going to move on just because of time. But we'll answer your question in a second. But yeah, I'm going to jump over this just for now, just because time. And I think Boolean logic is one of those topics that it's pretty short. Usually also FSMs are no longer in scope, I also realized. So I'm gonna jump to, let's see, the memory section. I think Erin is presenting that.
All right, so this is the C and memory section. If you have any questions, just let me know. I'll answer them as we go. Okay, so you can like copy this down or whatever. The idea of the int x, just something conceptual, is when you do int x, you're allocating on the stack, right? Which really means, if you think about it in RISC-V, you have the stack pointer, and you're basically stack pointer is right here, and you do add I, SP, SP -4, and the stack pointer moves down. And that 4 bytes of memory is now where you can put your int, or like whatever, like 32, 73, really doesn't matter. And then likewise, when you do int star x or int star y, int star z in this case, you're going to still move that stack pointer down however many bytes you need for the address. And that's basically saying, hey, let me put an address here. And then the int part is just saying, okay, this address technically is an int, but it could really be anything. Like you could screw it up if you want. And then the idea is when you have this int star, just like a common issue I've seen in product 1 is when I say int star x or int star z, the name of the variable is z, it's not star z, and the type is int star, right? But I could have said void star and then later cast it to an int star, which is why sometimes when you call malloc or like realloc, it's going to return a void pointer. And some people have noticed you get a compiler warning and you cast it to an int star to get rid of that compiler warning if it's like enough space for an int. Finally, you can dereference these pointers, and that's the little bit of confusion is when you do int star, it means it's an address, and when you put a star on the variable like x or y or z, it's just going to dereference it. And what I mean by dereference is it's going to go to that value that x or y or z is holding and say, look at that address. I'm going to go to that place in memory. So then when you guys get your seg faults, you guys know like you might have like int x equals like 30. And then when you say int x equals 30, you're going to convert it to a pointer, and then you're going to dereference that pointer. You're going to go all the way to in memory 30, and then you're going to try to reassign that. And then basically just going to go like a couple slides in. If you guys notice, the low place of memory is text and code. So when you go to 30 in text and code, you're basically saying, hey, can I modify like my literal code 30? And then C is smart enough where it's like, wait, what are you doing? And you're going to seg fault, which is why a lot of, which is why you'll get your seg faults. And then it's actually a good thing, because if you could edit your own code in memory, then you could like create some weird exploits or crash the program. And see, even though it's pretty stupid, it still has enough protection to recognize I should not be editing my own code with like random gibberish. And then another operation other than star is the address, the ampersand signal. What it does is it looks at that place in memory. It's like, okay, where's this stored in memory? Because remember, I did the add I SP SP -4, and it moves it down, and that place in memory has a technical address to it. So you just get where that address is, and you're like, okay, let me have that 4 byte, maybe 8 bytes, depends on the system architecture, and let me put that into some other place in memory where it's allocated. And then finally, this is just some extra things. You cannot just dereference X if it's an int straight up, you'll error. You have to cast it, and that's the great thing about C. Maybe it's a bad thing, where you can literally cast anything to anything. And it's just going to be like, okay, because it's all bits and bytes. It's like, okay, fine. I'll treat it as a pointer. I'll treat it as whatever you want, and then do stuff to it. And then, of course, this can cause some headache because typically speaking, you don't want to cast an integer to a pointer and dereference it. You're going to get a lot of seg faults with that. But maybe if you're doing some really clever stuff, you can get it to work. Okay, and then arrays. So this is just one way of declaring a char array. Do not treat this as a string though, because this has no null terminator. So if you call like string copy to this, you're going to go into an infinite loop and you might crash the program. Another thing about arrays is when I say A is equal to address of A, they have the technical same value, but to the compiler, that's actually kind of slightly different, because with a thing called pointer arithmetic, when you do A plus 1 in a char array, it's just going to go to the next address of the next character. But if you do address of A plus 1, you're going to have that, it's going to think of it as like an entire 5-block array, and it's going to go to the next 5-block array. And why that's useful is if you have some like 2-dimensional fixed size array, address of a+1 can get you to the next like row or next column, while just do a+1 will just get to the next like actual value inside the array. And then to access elements, you do like a and then bracket whatever value, end bracket. Remember, it's 0 indexed. I believe Python and Java are both 0 indexed, so this is like some new stuff, but MATLAB is technically 1 indexed. So if you guys took E7, I come from ECE, so whatever. It's 0 indexed. And then remember, there's no out of bounds checking, unlike Java and Python. So which means that you can go into out of memory, but when you out of memory, you're not going to actually error. You can like modify other variables somehow. It can be a pain, but just remember it's not out of bounds checking. And then again, pointer math is weird. So if you have a pointer called b and you do pointer +1, it doesn't actually take the pointer like address and add 1 to it. It'll go to the next pointer. So like if a pointer is 4 bytes, and then your pointer address is like 0xc0, it's going to go to 0xc4 when you add 1 to it. Yeah. Yeah, so if A is a character array of size 5, a+1 will take, so A is kind of like an address, right? A will go to the next character. Basically, it's, you should look at it as a character array. It's like, okay, let me get to the address of the next character. The address of a+1 is going to, let me go to the next character array of size 5 and increment it over by 1. So let's say I have a 2-dimensional array, right? I have a character A5 and another character B5 and another character C5, all stored sequentially in memory. If I do a+1, I'm going to get to like where B is in memory. But if I do address of a+1, I'm going to go to where, that was terrible naming. Okay, let's say my second array was Z5. Then when I do address of a+1, I'm going to go to where Z is in memory. Well, if I do a+1, I'm just going to go to the literal where B is in memory. I don't know, does that make sense? Yes, no? Okay. Okay, structs. Structs are just basically, the best way to think about it is just like a giant contiguous chunk of memory, and then you can assign fields to it, and all the fields to the compiler is, hey, this is where this value is stored. But like there's nothing other special. It's not really objects. It's just like a block of bits and bytes. So then you use the dot operator if it's just a literal struct. When I say literal struct, I mean like struct student. You do student dot like age and you can access it. However, there's a very common thing, which is you want to use struct pointers. So it's like a struct address. So you have like a struct star student, then you want to use the arrow operator, and the arrow operator will dereference it and then do a dot to it to access the field. And then the reason why we have an arrow operator is because when we pass a struct through a function, what will happen is in C, structs are passed by value. So if you can imagine a struct having a bunch of fields, it's like this giant block of memory. So when I put this struct into another function as just a struct, it'll literally copy all the values and it'll just put it into the function. And when it copies all the values, when you make a modification to the like the copied struct, it's not going to modify the original struct, which is really annoying because we're used to this object-oriented programming where if we modify like a struct or like an object in some function, we want to mutate it to the original, which is why we have to use addresses. And when we use addresses, then we dereference it and we make the modification. Since we've only copied the address over, they're both pointing to the same thing in memory. And then alignment. Okay, so alignment is a bit confusing, but basically when you have a struct, let's say you have like struct int char and int, the char is going to get padded 3 bytes down afterwards, and then you're going to have your other int. What I mean by that is like, so like if I say like struct ABC, if I have like int A, char B, int C, unless you specifically told it to pack, this will be somewhere in memory, like let's say 0xc000. This will be 0x, so it's going to be 4 bytes down, 0, 4. And even though this is of size 1 byte, this is going to be active at 0, 8. Because C itself is 4 bytes, and the compiler or your computer, in order to read C quickly, it wants to make sure that C is always aligned. So something that C does is it's going to be like, okay, let's waste an extra, because B only goes at 4, right? 5 to 7 is just going to be some garbage. Who cares? But if this C could be at 5 to like 8, then it's going to be misaligned. When it's misaligned, it slows everything down. So in order to speed things up, they're gonna basically have these padding bytes, and these padding bytes will allow us to read C faster, which is like the motivation. But for us, we just need to care about this like little formula. The address of the field needs to be divisible by the size of the field. And of course, the size of the struct itself, it has to be divisible by the biggest thing. So like what I mean by the biggest thing is, let's say I have like a 40 byte member, then the size of struct will have to be divisible by 40, and I'll add that extra padding to reflect that. I'm not sure if this is in scope, but there is a pragma called pact, and basically it'll just get rid of padding. But is that in scope?
It's not in scope for the exam, so you'll see this in part 4. But basically, that's like where you're trying to optimize everything, and so it like gets rid of all that stuff. But just need to know.
We're always going to do like allocating like 4, never like 4, we can do it like 4.
No. Okay, so if this was if I added an extra thing called like superint, and superint will be like size of equals 8. Oh, this is bad color. Okay, if this was size of 8, instinctively you want this to be at 12, but it's really going to be at 16 because it's like every 8. So you're gonna 12 is not divisible by 8, right? No. Okay. Because the computer, when it reads like things of size 8 and it knows to read of size 8, it's gonna want to go to 8th alignments because it'll be faster, which is just like something to know. That's like the motivation of why it does padding. But it'll be whatever the size of the field is, or size of the field is what it's divisible by. Addresses are size of 4, ints are size of 4, so it's 4 is very common, but it's not necessary. Yeah. Oh, so char itself, it could be anywhere. So if I did like a char D here, you can be 0.5 here. So char doesn't really matter. What really matters is this int that comes after. This int needs the padding, the int C. Yeah.
So if you have super int, but then you have int after the super int, then that one would be 8 because that also needs the padding.
Okay, so if I had another super int or just an int, it would not need padding because if this only takes 8 bytes, this would be at place, it would take from like 16 to 23. So the int after would be at memory address 24, and 24 is divisible by 4. So it's fine. You don't add any padding because it's already at a place that's divisible by 4. The reason why the superint needed padding is because it's size 8. And when it's size 8, after this int, it's going to be at address 12. But 12 is not divisible by 8. So you need to go to 16 to be divisible by 8. Yeah. What happens if I what? I don't think it's all zeros. It's just garbage. Like you don't really do anything with it. It's just how you allocate the fields. It's just going to go down. It's not necessary to be 0. Like it's not. I think you leave the OS to like do whatever you want to it, and it might be garbage. It might be 0. It's still part of the struct, but when you access the field, it won't be used. However, if I do something like crazy, like let's say I do ABC dot B, and then I add 1 to this, technically I can access the padding bits or padding bytes. Because remember, this is just all bytes. It's just like an array of bytes, and you can index into it however you want. Yeah. Any other questions? Okay. Yeah.
So like if you have the char after the super int, then that would also be that short.
No, because the char, because it's 1 byte, can really be wherever it wants to be, right? Because everything is divisible by 1 because it's size of 1. So the padding is for the field itself, not the field that comes before it. So like when you want like a char that comes after, you need padding for a char. You really never need padding for the char because everything is going to be in bytes. So that kind of makes sense. Oh, so the superint address will be at like location 16. It'll be 16 to 23. This is like allocated for the superint, and the char will be just at 24. Because you don't need padding. Like it's the next available address. Like the way you want to think about it is you look at the next available address, and then if that is divisible by the size of the field, you just place it there. If it's not, then you pad until you are divisible by the size of the field. Okay.
So yeah, just want to clarify that we add padding to like put some off pointer like the stack pointer like this, and we just look at that see if the padding works.
Yeah, basically, you wanna see if it's divisible, and if it's not divisible, you add padding. Yeah. Are we good? Okay. Next thing is unions. Unions are like structs, but not really. The idea of unions is you have all these fields and you have enough space to allocate for the biggest one, but unions are supposed to, and I mean supposed to, like they're technically used for only one of the values at a time. So if you see there, I have like a union student, int age, char name 40, double GPA. I believe doubles are 8 bytes. I might be wrong, but the union will be size 40. But for example, if I do like student.age equals 10, technically the name itself will have like whatever the int of 10 is be, but everything will be also will be like whatever garbage. But so they'll override each other. So the idea of unions is you're only using one field at a time. Why is this useful? In embedded systems, they have limited amount of memory. So when you have limited amount of memory and you want to like reuse things, maybe a union can be helpful. When you have limited amount of memory and you have like, maybe you want like an int and you have 4 chars and you want to choose between like a char of array 4 and ints, maybe you can reassign them and you can say, okay, now that I've assigned all the chars here, let me just pull off the int. Could be helpful for debugging. But other than that, unions are not that used that often. And then the way you access them is exactly the same as a struct. So you do the dot operator when it's like the actual literal union. You do the arrow operator when it's an address. Yeah. Because it's a char of size or char array of size 40. So then that's like the biggest field. Yeah. Yeah. Correct. So then if I did like if I did struct ABC, I assign my super into something and I said, hey, can I have A? I'm only going to take like the first 4 bytes of it. But like it's going to be pretty much, you can treat it as garbage because you assign something and then you're just taking something else and it's just like, what's going on here? You know? Does that make sense? It'll store the super int.
Yeah.
Oh, it'll store the super int, but like int A will also be overwritten, so you can still access A. Like there's nothing in the struct itself that tells us, oh, A is filled out or A is not filled, but super int is. It's just something that the compiler kind of does, and then you put it in there. Yeah, it's just like a block of bytes again. Okay, and then memory. So this is just an overview of how memory works. Just stack goes down and heap goes up. When you guys did the project 2 and all your assembly stuff, you noticed when you did the calling convention, you did like add I, SP, SP, negative, blah, blah, blah. That just moves the stack pointer down. And then to finish your function, you do like add I, SP, SP, blah, blah, blah. Some positive number and moves it back up. And that's like clearing the stack. Most of the time when you have a function, you're going to store your variables on the stack. And so when you store the variables on the stack, it just moves the stack pointer down. And when that function is done, the stack pointer gets moved back. And all these values that you put on there are gone now. They're garbage. Something else can use them, which means that these values, when they're gone, you need some way to store them over time, maybe. Like what if function 1 is done, but you need that function 1's value for function 2, but they're not in scope with each other? What do you do? Which is why you have dynamic memory in the heap. So for the heap, you had to call some specific functions called malloc or calloc or realloc, and realloc needs to already have a malloc pointer. And the idea is now you go into the heap, and the heap is not going to get destroyed when the function is done. The heap is only destroyed when you say, let me destroy this with free. And this is called dynamic allocation. All these do when you call malloc or calloc is they return a pointer in which the OS has said, I've given you a block of memory to use it however you want to do. Please don't leave this bounds of memory. Technically speaking, you might be able to leave the bounds of memory and you might override into garbage, you might segfault, but that's like all undefined behavior. And then of course, realloc, just something to know is realloc will not always return a new pointer. It might return the same pointer because all realloc does is first, it'll check hey, do I have enough space to grow this block of memory? Like, am I not interfering with other people's memory? If I am not interfering with other people's memory, I'm just gonna expand that piece of memory in the heap for me to use. However, if I am, let me just clear this memory. Let me go to a new part of memory, and let me give you this huge block of memory for you to use. And then calloc, it just when you return that memory, it's going to be pre-cleared to 0, and the OS will handle that. Yeah. Do we implement malloc in RISC-V?
So you don't have to ever implement it, and the reason is just because right now, like middle school systems, like that common systems ever really like use the hardware. But like say if your system were like set up for RISC or running with software, then yeah, like it would be exactly the same way. In RISC-V or in the RISC-V project, because we're using a simulator Venus to do it, kind of like setting up the stack and keep as if an operating. In the details.s file, you'll see like a implementation, like a very hidden away implementation for malloc. But you don't have to. You can just call it as it's any other.
With that being said, if you're interested in how to implement malloc, 162 has a homework on implementing malloc. And it uses flexible array members, which was like a note in the slide. Okay, and then little versus big endian. Apparently, this is not that emphasized. It's just something good to know. So I'll just literally, for me, when I wrote the cheat sheet, I literally copied this diagram. The idea is that little endian, the smallest part in memory, like your A value, your address in memory, the smallest part is going to be the least significant byte. While for a big endian, the smallest part is going to be the most significant byte. So our systems, when we do like anything in like project 1, I think project 4 as well, like our standard computer architecture is all going to be little endian. However, the exam might switch it up on you and then introduce big endian, and then you're going to kind of have to just basically draw out all the addresses and what they look like. And the idea of big endian is just how things are stored in memory and how things are like looked at in memory. It's going to be slightly different. I guess yes, yeah.
Let's make sure big and
Yeah. It's not going to store things in reverse. It's just like for the values themselves. Yeah, it's like how you look at it and then how you put it in. Like, but like if you had an array, the second element of the array will always come after the first element of the array, address wise. Yep. And then I think that is it. Any other questions? All right.
Thanks for covering that. And with that, we're going to go a little bit more in detail into some of this memory stuff because it's been a little, computer is kind of being funky. But yeah, it's a notable point of confusion about like how memory actually works and what really like how it's actually all used. And so we're going to look a little bit at it. So I'm just going to talk a little bit about some of the, I guess, like diving deeper into some of those things. So Aaron mentioned that like everything is bits. So what this means when it comes to casting is that literally anything can be casted into anything. So in C, things are weakly typed, which means that things are typed, but the compiler will only complain at you if you have certain flags enabled. And so that just means like, for example, if you have a random, say 32-bit integer, you could cast that to be a pointer and it would just trust you on the fact that like you say, oh, you say you can do this? Cool, then we're going to do this. But presents both good and bad things because you can cast things and make it easier for you in that sense, but also can cause problems. It also means that when you look at the data, if you don't know the type of the data, you actually won't be able to tell what's being held at that particular position. So it's indistinguishable basically from any other data or data type of that particular size. So some base definitions, a character is always 1 byte, and this is how things are defined in the system. The minimum size of a character must be 8 bits, and that's what we're using, and it's determined by this set constant in like the system stuff. So how many bits in a byte can be variable depending on the system, but the base kind of whole idea is that like a character is defined as a byte. The character might change sizes. It might be more, it might be less. So you might have a character with 16 bits, aka 1 byte is now 16 bits, but all other data types that are like, oh, this like integer is 4 bytes, this integer is 8 bytes, this double is a certain size, they're all based on the character. So that's why we typically don't talk about like 32-bit numbers. Instead, we talk about 4-byte numbers because it's all based on the bytes. So a short is defined as 2 bytes, an int is defined as 4 bytes, and a long is usually defined as 8 bytes. This is some pretty standard ones. They might change depending on like your system, but this is what we work with. And a pointer is defined as 4 bytes and 8 bytes respectively in a 32-bit and 64-bit system. So why do pointer sizes change, and what really is a pointer? So pointers are memory addresses, like Aaron mentioned, and memory addresses address memory. So literally memory addressing. So they act as indices to certain bytes in memory. So memory is considered to be byte address. And so we'll see how that actually works in the next slide. So we have a really wonky looking array like this. Like typically arrays are a little bit more normal looking, but if you like kind of tilt your head, it looks like a memory diagram, right? So we're going to think of this as an array. And so this array is going to be of size m. So m elements. So that's going to be some number that's going to be all ones in binary form. And so we're going to label, okay, the start of the array is 0. That's the first index. And then the last index is whatever this thing is, -1. I just realized I made a mistake there. I will fix it later. And so if we were to index it normally, we have indices that look kind of like this. So it goes from 0 all the way to m-1 in terms of sizing for indices. I also realized m-1 should be 1 to the left, but in hindsight. And then if we were to turn it into binary, it'll look something like this. So, but binary is kind of hard to look at, especially if you have a really large array. So we're going to turn it into hex. And in hex, it looks something like along these lines. So if we go through, well, the first one are the indices in base 10. The second one are indices in base 2. And the third one is an index, or the indices in base 16. But what do the indices also look like? That's the question. The indices also kind of maybe look like possibly memory addresses. I don't know if anyone feels like that way, but when we look at it, that's what we can kind of think about, especially once we get into the middle section. So beyond just the 0 through like the singular digits. So let's call this array car array of size n. So if we have this, let's say, okay, in our case, a particular character is 1 byte, which we're going to say is 8 bits right now, because that's what we've been working with. So in any particular kind of slot, we'll have 8 bits worth of space to be able to fill with information, right? Because each character is going to be in one of these positions. So let's say we're going to index into our car array and at 0 and write a C in there. It's going to look something like this. So this is ASCII encoding. If you're wondering where the why that's C, it's because it's the ASCII encoding. It's one of the ways that you turn characters into like binary values. They just assigned certain values. So that's what we're using. So we've assigned C at position 0 in this array. Then we're going to go to offset 2. We're going to insert a 6. So you'll notice it's funny because also this is interpreted as a character and not as a number 6. So that's why we have an encoding that doesn't look like the number 6. And then we have going to 4, we're going to do C again. So that repeats the first one. At position 1, we're going to encode S. And then at position 3, we're going to encode 1. So yay, CS61C, but in like a really weird way of writing it. So we can see that like the first 5 elements are kind of filled in already. And this is pretty standard for an array, right? We can see like we have an array and we have a certain offset. So another way of looking at this without like, let's say, okay, well, what if we don't want to change our index? So what if we want to index all at 0? So how would we do that? Well, a way of doing that would be, okay, let's say we're going to assign a variable called, this is not proper C anymore, but we're going to assign a variable 0 array is equal to car array. And we're going to index at 0 array at position 0. So that's going to give us C again. Then the next step is we're going to assign a 2 array at car array plus 2. So this kind of heralds back to Aaron's whole like pointer manipulation and like array, like can literally shift the things around to be able to like access at different positions. And so if we index that 2 array at position 0, that's going to give us 6 at where our previous location was. And then 4 array, we're doing the same thing, offset of 4, C. And then 1, we're going to add a 1 offset here and then write to it. And then a 3 offset, we're going to write to it as well. So we notice the difference here between this and the previous slide is that all the indices are now 0. So why did we actually talk about all that? The reason is because memory addresses, when we kind of look at things, are literally just kind of these nicknames for certain positions in memory. So car array we know is a memory address, and then we access it through the brackets. So if we add to it, it's kind of like pointer manipulation in that sense. We say like, okay, car array is pointing to this position in memory. We're going to create a nickname that like also points there in memory. And now we're going to create a nickname that points to like an offset of 2, an offset of 4, offset of 6. So literally at all the other offsets. And so these are new quote unquote memory addresses addressing those particular parts in the array. So at these specific offsets. Does that make sense so far? Okay, cool. So, well, why does that actually matter? Well, like we said it before, memory addresses are address memory, and all variables are basically just nicknames for a value. So they're like a container. So if you remember for 61C, you have like the environment diagrams, kind of like that. And then they are handled in 2 parts. So they're first declared and then they're initialized. So they're declared in one place, so somewhere in memory, and then they're initialized to a certain value. And they sit somewhere in memory. So for example, local variables declared within the context of, say, a function that's not, or within the context of a function, it would live on the stack. So when it's created, it lives on the stack. And there are a series of in bits that are interpreted in a specific way. So again, if we inspect in memory, we wouldn't be able to tell what it is, but the system knows how to interpret it because we've told it how to. So how does this relate to memory addresses then? So memory addresses are just another variable type that looks a little bit different. Like we said, like maybe in star, they have the star with them, but you can think about their name. So like say, for example, a car pointer, or a car pointer, and then we have like a name for it, pointer. That pointer is literally just another variable that happens to hold a set of bits that are interpreted as a memory address. So it also has its own memory address, which can be done with, for example, ampersand address. And this is something important to keep in mind because on past exams, there have been questions, for example, of saying, okay, where does address or pointer live in memory? Okay, cool. Where does star pointer live in memory? Where does ampersand pointer live in memory? So there are a lot of different ways, and that's why it's really important to have distinctions between these, because they could potentially all be different places in memory. So I'll go over that in a second with some examples. So, and then again, pointers are sized depending on the architecture. And the reason for that is because 32-bit memory is defining the fact that the memory can be addressed using 30 bits. So therefore, or 32 bits, which means that the pointers themselves have to be 32 bits, and they address 2 to the 32 bytes of memory. And same with 64-bit, but 2 to the 64 bytes of memory. So pointer arithmetic. So because we can do arithmetic, sorry, I'm speeding through some of these slides because of time. But if we can do arithmetic on literally anything else, so we can add to a car, we can add to an int, obviously, we can add to a Boolean. So why can't we add to pointers? Well, the short answer is, yeah, we can. Like if we have like an int I that equals some value, we don't care, and then we increment it, it increments I. So if you have a memory address and then you define it, say let's to be ampersand I. So it takes the address of where I is. Let's say I is on the stack. It's a stack address. And so we have a pointer that is defined as that value anymore. So it looks for I in memory, takes that memory address, and now plops it into this container. And then we try to increment that. Valid or not valid? Yes, no? No, I see a couple of no's. I see also confusion. I see tired faces. That makes sense. It's been a long day. So, oh no, I didn't actually. I seem to have not animated it correctly. Sad. Well, okay. So yeah, do we change the value that's stored in int pointer? And I guess all of the bullet points are now going to have spoilers. But yeah, because int pointer is a separate variable that just copied the address over, like the value of the address over, and just is a set of 32 bits that's now considered to be a memory address. So say if like the int pointer was like, say, some hex digit like that ends in 8, incrementing it would just now make it end in 9. So now it's no longer a correct address for I, but that doesn't matter because it's a separate variable. That makes sense? Okay. Oopsies. Sorry, what? No, it doesn't change I, yeah. It just changes the pointer because it's completely separate. So then the next question is, well, do we change the location of the pointer? And no, the location of the pointer, you would have to alter ampersand int pointer. But the int pointer itself is just a variable box that's carrying some other set of bits. But to change the actual pointer itself, you would have to do ampersand int pointer and then increment that instead. And then you would have to set, so you would have to do something like ampersand int pointer is equal to ampersand int pointer plus 1 or something along those lines. So then that's like literally changing where it is, but that's bad coding convention, I think. And then the last one is, well, do we now change the location of I? So that's the spicier question. And no, we don't change because we've copied the value of ampersand I into int pointer. So again, like everything is copied over. So it's not like, oh, now I'm suddenly like pointing to this. And so I'll be able to drag the value along with me. It's just copied and that's all. So I'll have to alter like where I is sitting in memory. Then you literally have to like change the it with ampersand and then reset all the values. Are there any questions? Yeah. No. So ampersand, you would what I mean is like you would just have to use ampersand I if you wanted to change the values, for example. So ampersand I just takes the memory address. So it's like if you want to do ampersand I is equal to ampersand I plus 1, then like, or something along those lines, then you would like quote unquote reset the address of I. Yeah. Okay, so the consensus on pointer arithmetic. Nick doesn't like it. He really, really hates it. Sometimes it's necessary. For example, if you want references to certain, like, for example, if you have a car pointer and then you're like, oh, it's pointing to a series of other cars. If you want to like do a linked list style kind of iteration or like change things around, you're gonna have to have offsets of some kind. So you do need pointer arithmetic to an extent. It's just avoid it when you can, basically. Okay, memory function calls. I'm gonna go through this really kind of speedy and I will do less of a back and forth than normally in discussion just because time. But basic, compiled versus interpreted, we already talked about it. Use a substitution, blah, blah, blah. Okay, I'm gonna skip through all of these. Yeah, memory is contiguous. It's separated into 4 chunks top down. We saw that in the diagram earlier. So stack goes on top and then heap, static data, and then text code. It has some kind of permissions, so different positions in memory have different types of permissions. And what permissions basically allows like the operating system telling us as users what you can do to certain parts of the memory. So for example, if we're writing to an array, that section of memory has write permissions, and we'll probably also read from that position. So we also have read permissions on that section. But we might not necessarily, for example, have executable permissions because if we're a bad guy and then we write something bad in there, we could like, for example, shut down our entire mega million system if we're Amazon or something like that. So some common, like there's read-only memory, which is ROM. So that is, or ROM. So that's typically stuff like code, which or like I would say it's static data, actually, like static data that are constants that you won't ever change again. That would be read-only. Read-write memory is probably like stack and keep, stuff like that. And then read-write-execute memory doesn't actually exist because this opens up a whole can of worms of like, for example, like the bad guy example earlier. You'll hear more about this in 161 if you choose to take it. But code memory will have something along the lines of read and execute memory, or read and execute permissions. So you don't want a combination ever of all 3 of them at once. And you also don't want write and execute because you don't want to be able to change something and then be able to execute it as well. But this is also beyond the scope. It's just interesting. So memory structure, we're looking at, if you remember from earlier, this is just like a turned around version of our array that we saw. So it starts from 0, goes all the way to all Fs. And so we start from code text on the bottom, static, heap to stack at the very top, and going through each of the different sections. So the part that's highlighted right now, we can see that that's the code and text section. And this is the code that you intend on executing to and that you shouldn't be editing as you're executing. Some exam questions in the past, you'll notice like have self-modifying code. And that's stuff you'll typically see in the context of like exams, or if you're really, really brave, or if you're doing something like funky. Yeah. And then this usually includes some constants. So we know that like constants, they're typically thought about as like being in static memory. What kind of constants do you guys think would fall under code or text? Thought? Huh? Function definitions. Those aren't exactly constants. So constants are things that are clearly like values, like 1, 2, true, false, stuff like that. Yeah. Strings. Sure, yeah, strings count as constants when they're there. Yeah. Huh? So It depends on how it's like written, I guess. I will talk about that in a minute. Yeah.
Like, I think like some like size of, like, it's like how large.
That's a function, so it's calculated on the fly, so it's not really stored in that sense. Does that make sense? Zero. Like null pointer?
Yeah.
Oh yeah, okay. So yeah, null pointers, they're just, yeah, because they're just a byte of all zeros, so that would be stored there. So things that would be stored here, for example, would be if it's incorporated into the code itself. So like, for example, if you have x is equal to y plus 1, the plus 1 doesn't have another way of getting referenced, and it's like literally embedded in the code itself. So you can't have another say of like, oh, I'm going to reference this from somewhere else. So that would be stored directly in the code. So like a good way to think about it is like, for example, if you translate a section of code into assembly, is that going to be an immediate? And if it's an immediate, usually it's going to be in the code section. Does that make sense? Okay. Then this next bright pink section, we have static and data, and this is primarily constants that don't need to be changed, but sometimes they might be changed. And so this is usually a random access memory. So what this means is random access typically just means you don't have to load all of the previous bytes in order to access something else. So this is one of the most standard types of memory nowadays. So I'm going to skip over this part. So not as important. The next section that we're going to be looking at is the heap, and the heap is memory that's dynamically allocated. You've heard this multiple times at this point, but dynamic allocation is just us asking the systems to say, I need a chunk of n bytes. Can you give that to me? And if there are n contiguous bytes, then yes, it will do that. We'll talk more about dynamic allocation in a few minutes. And it's typically not executable because we should be writing to the heap. So this is something that must be free. So this still exists when we do our RISC-V project, because sometimes you'll malloc things, you'll still need to free those. So any memory that has been malloc, calloc, or realloc needs to be manually freed. Otherwise, you're going to get memory leaks, and that's not great. So this grows bottom up, or bottom up. What this basically means is like if we're looking at this giant chunk of memory, typically like you can assume that it grows from like the bottom and tries to allocate as it goes up, but because things can be freed and they'll quote unquote be given back, it's not going to be linear. So I'll show you an example of that in a second. So we're going to say heap pointer starts here, and then hello, there we go. The stack is memory that's automatically allocated again, and it's read write. It will be freed by the system automatically and grows top down. So remember, when growing top down, what that means is we start from a higher memory address, and to allocate more memory, we're going to subtract the memory address because it gives us more space. And to kind of put it back or to restore the stack pointer, we add it. So, okay, stack pointer starts up there. We're going to go through a step through a function call. So Aaron mentioned earlier, like we change the stack when we call function and we store it when we're done. But how does that actually work? Well, if we have a dummy function and then we have a main function, we're going to enter through the main function. And the very first thing that we do is we want to make sure that the arguments are set up. So when we kind of look at this, we have declared arguments arg1 and arg2. Where does everyone think that where do people think they'll go in memory? So which one of the sectors right now? Stack, I heard stack. Yeah, that's exactly right. So we have arg1, arg2. The reason that they're in one line is because I realized too late I had too few square or rectangles, and I didn't want to go back and change like 15 slides. So yeah, but arg1 and arg2, because they're in their 4 bytes, we're going to consider the rest of these to be all 4 bytes each, but that one's just kind of an anomaly just because spacing. So we have arg1, arg2 pushed on there. Cool. Now where are 1 and 2 stored? I heard one vote for static. Any other thoughts? So this would actually get stored in the code, like that. And the reason is because if we try to translate this into assembly, it would be something along the lines of like, for example, move A0, 1, move A1, 2, or something along those lines. And because we don't have another reference to 1 and 2, so instead what happens is like we know arg1 and arg2 have values that are in the code themselves, and they'll kind of get copied over eventually. So there's a lot of copy pasting kind of going on. But they know because of the executable that they're referencing memory that's in code. That we good on that? Yeah.
So, since R1, R2 are like being declared outside the function, why are they not static?
What do you mean declared outside the
So
function?
like you're not calling dummy, like you're declaring, you're initializing between R1 and R2 like before you call the dummy function. So like why would it not be static? It doesn't work all the
Yeah, so main, the reason is because main is also a function. So to be in static, yeah, I feel your pain. But so to be in static memory, so like a variable, like it has to be global, which is outside of any memory. So for example, if like it were declared up here or like in between these two lines, then it would be in static. So that's a great question. Yeah, it also brings me great pain. Okay, so now that we're actually calling dummy functions, so the underlying things are the ones that we're looking at right now. So we call dummy, and we're focusing on args1, arg2, or arg1 and arg2. Does anything look weird to you guys, or just something that is like this feels wrong, but I don't know why? Just letting you know it's correct right now. It's just some things might feel strange. Huh? The names. arg1, arg2, like they seem flipped, or do I see a hand back there? Are you stretching? Oh, sorry. Okay, so one of the things, I think that this was asked earlier, but this is the concept of like when we're looking at, oopsies, when we're looking at arg1 and arg2, we're used to looking at like, oh, arg1, arg2. So why wouldn't arg1 be here and arg2 be here? And no, the reason is because when we're allocating space on the stack, it goes down. But in that chunk of space that we just allocated, so the dark red color, we read bottom up. So the first element that we want to read goes from where the stack pointer is now. And the second element starts from like one section up. So to be able to read our, like know that the first argument is arg1 and the second argument is arg2, we have to push them onto the stack in reverse order. That's why it looks upside down right there. We also noticed that this old stack pointer is up here. It's kind of like faded out. So is up here. The faded out sections are things that are outside the scope of our current function. So that's stuff that you could technically alter and technically touch, but it would be very bad convention to do that because it's not related to your current function. Does that make sense? Yeah. Yeah, so like to us, like I guess first like the argument names, like part of the I guess this is starting to look like 61A naming convention. But yeah, so they're the same quote unquote values, but remember like when we talk about calling functions, that C is a pass by value system. So that's why like you see it repeat multiple times. If it were passed by reference, for example, it would be slightly different. But yeah, so now moving on. So now we're actually going to go into the function. So you'll notice a couple of things first to go on. The stack pointer that we literally just had is now faded out because we've now created more temporary registers, or sorry, temporary variables, local variables, not temporary, local variables. And so we want to bump the stack pointer down to accommodate for that. So we see temp is in there and its variable is referencing whatever is held in argument 2. So that's why like there's a small little kind of pointing there. So it's saying, oh, whatever argument 2 is taken, I'm going to copy that. And so now what happens after that is once we actually finish that stage, then we're going to return. So arg1 and arg1 plus temp is something that's going to be calculated and eventually returned. But because it's not stored in another variable, we don't see another section being allocated on the stack for it. This might be the equivalent of, for example, putting it in a temporary register in RISC-V, and then putting it in say A0 as a return value. And then while you're adding it to put it in a temporary register. So it's not creating extra space on the stack. It's just using stuff that you already have available. And then once we return that, we see we bump the stack pointer back to where it was before. And everything below that is now out of scope of our quote unquote current function, which is now back to main. But we can see that the values still are there. So kind of common confusion is like, is it overwritten? Is it cleared? Neither really. It's just kind of sits there. It's just we don't have access to it anymore, which is the important thing to pay attention to. So theoretically, if we like bump the stack pointer down and try to read through all of that, all the values would still be the same, assuming nothing else has executed during that time. that make sense? Okay, so I'm gonna go through the next kind of example a little bit quicker because it's mostly the same. The main change that we can see is that malloc happened. The thing to pay attention to here is where temp is, where eventually the thing that is holding is, and I'll point that out as we go. So we notice that we're loading our stack frame with arg1 and arg2, and then we have a temp variable. So we can see that temp is a pointer and it's holding some value of malloc. We haven't executed malloc just yet. We've just declared temp. And can anyone say like why is temp not in the heap? Yeah. Okay, so when we call malloc, we're going to move the heap pointer and not the stack. That is true. However, like why is temp, like for example, not like in this section? Why is it up here? Yeah.
Because like temp is just like it will just return the address itself would be stored on the stack. Because the address just points to stuff on it.
Exactly. Yeah. So you can see what happens here. So let's actually call malloc and see what happens. So our malloc is going to give us some heap address. So it's the really dark blue part, and then our heap pointer kind of is moved. So this is all a very like large overview version of looking through all of this. It's a little bit more complicated as Aaron referenced earlier, but we can just kind of think about it like that. So we can see that temp itself is on the stack. It's storing some kind of value, which is the heap address pointer. It's some 32-bit value. And then the heap address pointer is somewhere in this kind of heap. And eventually when we set like temp, for example, maybe we do temp star temp is equal to 3. Then 3 will be stored here eventually. So the value will be stored here. This is the heap address temp, and then this is what it's storing up here. Yeah. The heap to this address. It's well, okay. It's as absolute as you can get. Yeah. Okay. So moving on to this. Okay, I guess I just totally skipped the setting of the values. I should have done that. I realized I apparently missed the slide. But yeah, if we execute, like for example, the star temp equals arg2, then this is going to be going to have arg2 down here, the value of that, and then once we return it, then we're just going to still have that. So the question then here is like, what happens to heap address temp? Well, it's not freed, right? And so now it'll live on the heap forever, and we will no longer be able to use it because we now no longer have access to temp, which is holding the heap memory address. So now it's not freed, it's not in the free list, and we don't have access to it. So this is what a memory leak kind of looks like. So it's just kind of in limbo now. So well, what can we do to fix that? We're going to do something like this. We're going to just return the variable instead. And after we return the variable, then we'll be able to free it. But it also does change how the stack looks a little bit, because what will happen here is like now, okay, we've concluded we're returning temp. We now no longer have access to temp, arg1, arg2. But now what we're going to do is we're going to assign that output to a temp pointer. And we can see that that overwrote that particular section. So because now we're back in our mainframe, we're using the same stack. So we don't differentiate between whether or not like, oh, there was something previously here or not. All we know is like in main, we want a new variable, which is temp pointer. And temp pointer now is holding that heap address temp. So you can also see why returning temp is not an issue, because we're just returning the value of it since it's passed by value. But if, for example, we wanted to return if we what's a good example? If like temp were an integer. Okay, if temp weren't malloc and it was on the stack itself, then we can see like why it would be an issue, because it would be like stuff here and that we no longer have access to. So it'd be trying to like point to something down here. So now that we have that, and then we call free temp. Okay, this should have said temp pointer. I think I forgot to change that. But now we can see that once it's freed, now it's kind of pale blue. And so now we're all the way back to where we were at the beginning. Yeah?
So dummy is returning temp, which is 3, and then the pointer, temp pointer is pointing to the address of where 3 located, which is something.
Yeah, exactly. So yeah, for online, what was said was basically like when we have this temp pointer is pointing to an address on the stack or the heap, and then the position on the heap is going to have 3, because that's what arg1 and arg2 added up to be. Okay, so there's a different way to actually do this. I guess why doesn't HP return to the original position? It's because the heap isn't used linearly. We'll talk more about this in a second. There's an alternate usage pattern. I'm going to do this at the very end if we have the time for it. This is just like, where's it now? There we go. So this is just a way of like leveraging things like if you don't want to use malloc, how can you like still pass that through that? I'll talk more about this later. Let me jump to. We're gonna go skip these. Okay, we're gonna jump to type defing because I think there was a lot of confusion about that when we first started. So I'm just gonna go over it for a second. So it looks something along these lines. So this is how you would typically define a structure. So LL node, for example, linked list node. This is how you would type def it. Oh wait, no, it's not how you would type def it. I'm dumb. Sorry, I am going to update this right now because this was not good. There we go. So yeah, you would have a type def keyword, and then you notice at the very, very end, there we go. At the very end, we have a nickname for it. So now it's capitalized and it's a shortened version that's a little bit more clear. We don't care about the fact that it's a linked list. And the reason that we use it is because it's used to create a nickname for certain values or structs or things like that. And it's usually used for when it needs to be external facing because sometimes like the user doesn't need to know exactly what went into this. So for example, here, if it was slightly more complicated, like maybe we were like, oh, it's a linked list node that has like a sentinel or something. It might be like LL node sentinel or whatever. Like the user doesn't care about that. All they want is a working implementation. So that's when type defing might be useful. It's used to make things cleaner. In code, it's a little bit more obvious. And then you might also wonder like, oh, well, isn't it the same thing as define? Because define is also like, define does something like this. So # define 1 is going to be referencing 1. So they both give nicknames to values, but type def can only give symbolic names, whereas so like these are like symbols, whereas define can actually define certain values, like for example, defining a 1. You can't do that with type def. So type def might look something like this. Type def unsigned character as a singular byte because a character is a byte and we want to unsign. So we could do something like that, for example. So type defs are interpreted or quote unquote interpreted, translated by the compiler, and define is substituted in by the C processor, like we said before, or C preprocessor. Okay, that's not super important. We're going to jump over unions because that was already covered. We're going to so define is a lot more flexible than the type def basically. So you can like substitute values in. We can substitute like you can literally define like for example a function using a define. So you don't have to worry about like all the different breadths of it. It's just it was something that might have been confusing why certain ones might be used. Okay. Okay, I'm going to jump into dynamic allocation really quickly and run through an example before we jump into the next section. So memory located on the heap must be manually freed before you return from main. Otherwise, it'll cause memory leaks, aka memory that's in limbo. There are 3 types: malloc, which stands for memory allocation. Calloc, which stands for cleared allocation. The cleared part represents basically the chunk of memory that you get returned. All the bits have been set to 0, and that's really useful. For example, if you have a struct or a union or something like that, that has like the default values to all be 0. It's really useful for that, so you don't have to go through manually set all of them. And then realloc stands for reallocation, and this basically is you have a pointer of like n size, and then you're like, oh wait, I like kind of maybe want to reuse this because I don't want to fragment my memory, which basically means chopping it up into a bunch of tiny pieces. So instead you're like, okay, I'm going to see if I can fit like this particular like something that's n sized within this n size and see if the system will let me do that. Otherwise, I'm going to ask the system for new memory. So it's not always allocated linearly. So So think of memory as like a band that we just saw, I guess, as a so basically what the system does is if there's a contiguous chunk of memory that's at least as large as what's been requested, the system will return the pointer, any metadata that's needed. Otherwise, it'll return null. And this is important because even if there's overall enough memory left in the system that's free, if it's not continuous, aka like the memory addresses aren't like in order for the chunks, and there's no break in them, then it won't be returned. So it might be easier to see with an example. So let's allocate some memory. We're going to use color-coded arrows instead of letters because it populates the screen a little bit less, but let's say our heat pointer starts here. So this is where we're going to start allocating memory from. This entire band is just continuous memory that nothing has happened yet. So our first request is going to be pink. So it's going to be an A-sized memory chunk. And we have that amount available, so we're going to chop it up and then give it to us. So all the colored pieces are now considered to be used. So the result of this is, okay, now we're going to bump the start of the free list to the end of the pink chunk. So now we know that the first chunk is not available. We've returned the pointer to that, the pink pointer to wherever it was needed in memory. And now our free list has been updated. We asked another request. It's going to be a B-sized memory chunk. Similar thing happens. We have it available. We're going to pass it back, and then we're going to update the pointer. We're going to go through a couple of these just because there's quite a few. So we're going to start of free list. So the free list is just all the non-colored chunks. Yeah. Yeah. Oh, like freeing the list. Okay, yeah. So yeah, this thing is a free list in of itself, but not freeing the list. Yeah. So we're gonna just allocate. So you notice something that's important about this is like we had one really big chunk in the beginning, which is great because it's all one request, and then we had a bunch of really tiny requests in the middle. And right now it's pretty okay. Like we don't care about that. Yeah, but we asked for another really big chunk, this really bright purple one. And that's going to be our last request for now because we're done asking for memory. So does anyone see any issues potentially pop up with the way that we've requested our memory? Yeah, so that's touching on a bigger concept, but that's absolutely correct. So if we wanted to say call reallocate on the yellow, really tiny sliver in that middle right here for something bigger, then that becomes an issue because it's bigger than what's allotted, and all of our forwards and backwards are now like set. So instead we would have to free this, and we would have to allocate from this section. So that's touching on a bigger issue of fragmentation. So what we're going to do is we're going to free the green. So freeing the green would cause it basically to become white. And now the green chunk is now part of the free list. So this is all fine and dandy. So if we wanted to re-request that, might actually work, or something of a smaller size. But we noticed that like it's separated by the purple and then the more aggressively purple chunk. And so it's not contiguous anymore. So if we wanted to request, hello, there we go. If we wanted to, I realize you guys can't see this. Move this over. So if we want to request an A plus D size chunk, so okay, if we look at this, a chunk that's those two sizes together, would we actually, we might actually not be able to do that. And the part of the reason is I realize also my sizing might have been off. So I'm going to clean this up on the finals presentation. But if we want to copy it over to over here, okay, we see that it does fit in this section. But say if we add this section, we're going to pretend that this section is like a tiny bit large, just for the sake of presentation. I realized I didn't actually measure it correctly, so it might actually fit. So if it actually did fit in this section, it would be great. But assuming that this is a tiny bit larger, and like if we try to like measure it to the end of this, maybe it like just slightly goes over. And so we can see that overall total, we do have like this free in our system. So we have this chunk and then plus this chunk, but because it's not contiguous, it won't actually return as an okay, and so it'll return null instead. So it fails. Does that make sense? Yeah. Yeah. Continuously. Yeah. So you can't guarantee that. So this example is using this kind of allocation method called first fit, and what that means is basically we literally just look through the kind of free list linearly and say, okay, this is the first like slot that we can fit this memory request into, and so that's what we'll do. Basically, there's also a couple more that we won't touch on. It's called like next fit, random, best fit, the buddy system that was mentioned in the lecture, etc. But this is one of the like common ones to use as an example. So, was there a question back there? Okay. So yeah, the suggestion was, okay, what if we literally just say, okay, we're gonna request this part and then this part, and then we're just gonna kind of stick them together. And the reason is like it's kind of twofold. So one of them is being like, well, what if we just try to merge those? And merging doesn't actually work because memory like indices are like continuous. Like if you were to use certain parts of an array, you couldn't just merge the unused parts of the array because then it repeats indices, right? So memory kind of works in that way as well. And the kind of second thing being like, okay, why can't we have like meta memory that points to the two sections? And I guess the simple answer is just like it's too complicated because like at what point like will you stop being like meta, right? Like for example, if you run out of like meta slices, do we have one more layer? Yeah. So it gets really complicated real quick. Any other questions? Okay. We're gonna jump into section 2. Do we want a slight break as well? So we're gonna probably run until 5, to be honest. So this last section will be slightly less like heavy, but we'll take a break until 3:02, 4:02. Sorry. Yeah.
All right, guys, let's get started. You guys forgot, my name's Chris, and I'll be going over number rep. Based off our survey, it seems like most people understood it relatively well, so we'll try to keep this short and sweet. Oh, do you have to click it? Oh, is this the, oh, this isn't the actual, oh shoot, my bad. Whoops.
There we go.
Okay, thank you. My bad. So yeah, key idea, everything in computer is just bits. You guys have probably heard this before and definitely won't be the last time you guys hear it. And so I guess what that means is there's different ways to interpret these bits, and that's ultimately the main question. So these are some of the few ways that we can interpret bits. There's binary, there's our ASCII characters, our hexadecimals, base 10 and 8-bit 2's complement. These are definitely not the only ways, but these are probably the main ways that you will encounter them in your exam. Binary is pretty straightforward. ASCII characters, the main way I did it was Google a table and then see how that converts. On an exam, you'll probably get the conversion. I don't think you'll be expected to remember all of these. Hex, the easiest way is to take 4 bits in binary and then convert that to hex. And then base 10 is our typical decimal, and then 2's complement we'll cover pretty soon. All right, so here's some quick tricks. If you want to represent a power of 2 in binary, literally each of the slots in your binary value are a power of 2. So going from right to left, it's 2 to the 0. And then depending on how many bits you have, then that's how we would represent it. And then to represent one less than the power of 2, we would take our first trick and then we would subtract 1 in binary. That would just be our first value on the rightmost bit. So then we would do that, subtract 1, and we would get 1 less than the power of 2. And then another thing we want to keep track of is just representing negative numbers. So when it comes to negative numbers, we have many ways to represent negative numbers. For unsigned, it's all positive for the most part. And then 2's complement. This is a way we can convert our positives to our negatives, basically splitting our values and having some of them as negative. And the way that works is we invert all the bits and then add 1. That's how you convert between positive and negative. And then bias notation. Bias notation is a way where we set a bias typically down the middle so that we can have a relatively equal number of negative values and positive values, although the bias does not necessarily need to be the exact middle. So bias is just a way of shifting all our values so that we can have some negative values. And then next, here is a question from fall 2019. What you want to do is take the binary /hex in the middle and then convert that to the negative value. And if it's not possible, then you want to write NA. And I think giving about, say, like 3 minutes for that should be reasonable. But if you guys need more time, definitely let me know. All right, let's get started. For the first one, we're using an unsigned representation and the binary hex is right there. Does anyone have any ideas as to what the negation of that would be? Yeah, go ahead. Yeah, that's correct. So since it's unsigned, we can't have a negation of that. So, oh shoot. Well, there's all the answers, but I guess I'll just give a quick explanation for each of these. So for the second row, our value is it's 4. So then if we put the bias into that, we'll get -3. So essentially we want to find 3, but then we also have to include the 7 bias. So that's why in binary we'll do 3 plus 7, which is 10, and then we'll have 8 and 2 with the bit as 1. Same idea for OXF, except when we do OXF and we subtract 7, F is 15. So if we do 15 minus 7, we'll get 8, and -8 is outside of our range because if the smallest value we can have is 0, then -8 is not representable. And then 2's complements, both of these essentially work the same way. It's just that one is in binary, one is in hex. And what we want to do is take all the bits, invert them, add 1, and then we should get the values in the negation column. All right. And then here's some cheat sheet stuff. So first of all, n bits can represent 2 to the n things, and that's typically from 0 to 2 to the n minus 1. Although it's not always exactly those values, given that we can have our bias, or I think there's also a very interesting note on discussion 1 where it says that there's not necessarily a highest integer you can represent with n bits, given that you can use it to represent many different things. And then, yeah, so 2's complement and sign bias are probably the most common ways that will negate things. But at the bottom here, 1's complement is also a thing. So from this year's lecture slides, it goes into a lot more depth, but when I took it, they basically said you didn't really need to know 1's complement. And besides that, I think for the most part, binary and number representation, for the most part, it's relatively straightforward. I would say that just know it well enough where you can see how to convert between different values. And yeah, just don't let it become a bottleneck during the exam because they're relatively straightforward, especially for midterm 1. So with that, we'll move on to floating point. And yes, with floating point, so here are some common questions with floating point. And these are very similar to the homework. I believe it was homework number 3 or 5. It was homework number 3. Yeah, so on homework number 3, there were many questions like this. And yeah, the main thing to understand when doing questions like this is just how are floating points represented and how can we maximize or minimize these values? So here's the representation of floating point. We have our sign, we have our exponent, and we have our mantissa. And yeah, I think the main thing to keep track of is the table on the bottom with the exponent, significant, and the meaning. This is probably the most important thing to have on your cheat sheet, along with the formulas right above them. And yeah, so using these values is the way you can convert between that and your other floating points. And yes, it'll come up and give a quick example.
Okay. Yeah, hey, I'm Sid. I'm an AI. So I guess we're going to be walking over a question on floating point from spring 2019. So yeah, so oftentimes in these problems, they'll give you some kind of modified floating point scheme and ask you some questions. So yeah, so there's 3 parts to this question. Part A, what is the new bias for our floating point scheme? And we change our scheme so that we have 7 bits for the exponent now instead of 8. And now we have 24 bits for the significant instead of 23, right? Okay, so now we have to calculate some stuff. So for the first part, what is the new bias for our floating point scheme? So if you think about the bias, what is the purpose of the bias? Well, the idea of the bias is it should allow us to express negative exponents equally well as we're allowed to express positive exponents, okay? So essentially we want to center our exponent around 0 when we use a bias. So if you use 7 bits for our exponent and we consider that to be unsigned, what's the range of values that we can represent? Well, we can represent from 0 to 2 to the power 7 minus 1, which should be from 0 to 127. Okay, cool. So that means the bias that we need in order to center this around 0 is negative 63. So that way we represent values from negative 63 to 64, which is centered. So yeah, so there's also a formula that you can use, which is expressed in these slides, which is the negative 2 to the power 7 minus 1 expression. So that should be generalizable to like many other problems that you might see on exams where you have n bits for your exponent. So that's definitely a good formula to keep in mind on your cheat sheet. Okay, problem B is asking to represent 18.75 in our new floating point scheme. So there's a couple of steps to solving this problem, and I'll just walk through it. So the first part is to represent the number in binary. The second part is to normalize so that 1 number is before the binary point. So that's kind of like scientific notation, how you might represent 637 to be 6.37 times 10 to the power 2. Okay, give me an example here in binary. We'll calculate exponent bits. So figure out what you want the power of 2 to be. And here are some specific rules as well for the exponents. Definitely no denormalization. And IEEE 754 has negative 127 as the bias. But okay, this isn't true for this example, right? Because we have negative 63 as our bias. So I'm going to set the sign bit. Remember, sign bit is set to 1 if you want to represent a negative number, 0 if you want to represent a positive number. And then lastly, you just want to piece it all together, like the sign bits, exponent bits, mantissa bits. Yeah, so step 1 is to convert 18.75 into binary. So here what's doing is 10010, that's 18, and then decimal 11 is 1/2 plus 1/4, which is 0.75. So that's how it computes that. Then okay, now what we're doing is we're shifting the decimal point so that we get it to be right after the first one, right? It's like scientific notation. Cool, and that gives us our mantissa. The mantissa is basically what's after the decimal. And we also find our exponent from that, which is 4. So now that we have our exponent, we have to find the exponent bits. And remember, since we have a bias of -63, it's not so easy as just saying like 100, right? We have to add the bias or take that into account. So really what we want to be representing is 67 for our exponent, because 4 plus 63 is 67. So that's 64 plus 2 plus 1, which as you can see is the exponent bits. Cool. And then since the number is positive, we're going to just be using our sign bit to be 0, because 0 represents positive floating point values. Okay, and then lastly, we just have to put all this stuff together. So sign bit, exponent bits, mantissa bits. So yeah, so here's that just all put together. We put the sign bit, then our 7 exponent bits, and our 24 mantissa bits. Yep, and we just had zeros at the end of the mantissa because we don't need those. Yeah, cool. Awesome. Okay, what is the largest finite value you can represent in this floating point scheme? Okay, intuitively, what you want to do whenever you're trying to maximize the value you can represent, or the finite value you can represent in floating point, is you want to set your exponent to be like as high as possible, and you want your mantissa to be as like big as possible, right? But we can't really get too greedy here, because if we set the exponent to be as high as possible, then we get all ones, which is infinity or not a number, right? So what we do is we set it to be 1 less than all ones, which is a bunch of ones and then a 0. There should be 6 ones and a 0 in this case, or exponent. And the mantissa, we're free to just set it to be as big as possible, so all ones. And so now we just simply have to calculate the value. Okay, and obviously since it's a positive, we want to represent a large finite value, so we take our sign bit to be 0 to be positive. Okay, cool. So if our exponent is all ones and a 0, what we end up getting here is 127 minus 1. Yeah, 127 minus 1 is 126. But remember, we also have to subtract the bias, so we'll do that a little bit later. So our mantissa will be 2 minus 2 to the power -24. There's many ways you can kind of think about how to calculate the mantissa. The way I don't really like to think about it in the way that's in the slides. Since our mantissa bits are all ones, that means we're basically 2 to the power -24 away from 2, which means 1 dot m is 2 minus 2 to the power -24. That's the way I like to think about it. But either way, once you get your mantissa and your exponent bits, all you have to do now is just put it all together. Cool. So the mantissa, well, 1 plus mantissa, right, is equal to 2 minus 2 to the power -24. And now we multiply it with 2 to our exponent minus the bias. So the exponent is 126, right, which you calculated, and the bias is -63, which you calculated earlier. Okay. So then when we multiply this all together, we get 2 minus 2 to the power -24 times 2 to the power 63. And the final expression is just using like the distributive property multiplication, and you get this result. Cool. Awesome. Yeah, so now we're on to risk 5. So yeah, I'll let someone else take it from here.
So do I just like
Yeah.
all right, so hi everybody, my name is Nikhil, and we're going to be covering our final topic in this review session today, which is risk 5. So C to risk 5, basically, as we talked about earlier with call, what happens that with the compiler, a compiler always turns like general C code or memory state code into an assembly language. Normally you will see x86 or ARM, but in this class we cover risk 5. And C constructs and 3 constructs get translated to assembly in predictable ways. And we can walk through a quick example right here. So if we have int s0 is equal to 0, we can simply replace that with the statement li s0 0, which basically sets the s0 register to 0. And then we have a while loop, which has the condition s0 is less than 4. So in order to do that, first we want to set a register to hold our number 4, which we do right here after declaring the initial like label. And then what we do is we have an instruction to make sure that we either keep going in the loop if our while condition is not met, or it breaks. So basically it's something like this: BGE S0 T0 done. Basically, if S0 is greater than or equal to T0, then we are done. And then what will happen is that we do a JAL do work, which basically calls the do work function. And notice how we use JAL, because we not only want to jump to the do work label or function in this case, we also want to return from the do work function and go back to our next lines within our current code. And then what we see here is that we do add I S0 S01, which simply adds the 1 to S0 so that it sort of represents the line S0 plus equals 1 in our code. And then we have J while, which basically jumps back to the while loop. And we use J because we're not worried about linking. I have another slide on jump instructions, and yeah, we'll go more into that a little bit later. And then we have our done, which is done label, which, as we specified earlier in our BGE instruction, S0 T0 done. It will jump to there when we are finished sort of iterating through the while. And a good way to tackle RISC-V code or RISC-V questions on an exam is to think about the C pseudocode first. This especially comes in handy when you're doing project 2A and 2B. I know it helped me a lot when I did it. And so I know that C pseudocode first really does help. Okay, calling convention. So the thing about calling convention in RISC-V is that we need to preserve the values of some registers, because in a certain function, we have to assume that another function may want some of those registers to be the same. And an example of that is S0 to S11, which are all the saved registers. And it guarantees that those registers have to be restored if we go back to the previous function, like they're the same. And the same with the stack pointer. And I guess a good example of this is because if we don't return the stack pointer to where it currently was, there is a very high chance that we are not going to be loading in the same value back, and we don't want that. And so as a result, SP is also, the stack pointer register is also something that has to be restored. And under calling convention, you must assume that RA, T0 to T6, and A0 to A7 were invalidated, which basically means that you cannot assume that they are all 0, or you can't assume that they have some sort of certain value. You have to modify these registers in a way so that it sort of clears any existing values on these registers that you can then use in your code. And we can use calling convention in this example of the myfunc label, which we can fix. So here we have LIT01, then we do JAL black box, then we have add A0, A0, T0, and then we have red. Does anybody want to point out any calling convention errors off the bat, right off the bat? Yes, exactly. So that is one thing, because we are not only using T0 before the JAL, we're using it after the JAL as well. We want that number to be the same. So as a result, we can't assume, we have to save that in our code. There is another very important calling convention error here. Does anybody want to point that out? Yeah. Yes, because we have to save RA, because JAL, what happens in JAL is that our RA register will be rewritten with the address of the next instruction in our myfunc label. And so it's important we do save RA so that at the end of our function, we can simply load it again. And then we can return to wherever we called the myfun label from. And so right here, let's see if I can move this to make this a little clearer. Yeah. Over here is basically what our correct function looks like, label looks like. Any questions about calling convention? All right, let's keep going. So, instruction formats. In RISC-V, there are a couple different kinds of instructions that you want to use. And the main difference between them is not only in how they're used, but also how they are structured in binary. So for example, we have the R, I. So for example, we have R and I. As you can see in the R instruction, there is a default like set of bits set for RS2, because you're basically adding RS1, or you're manipulating the bits at, or the values at the RS1 register and the RS2 register. However, in an I instruction, we don't care. We only need one register of the values that we're trying to get from, because the other one would be an immediate. And so that's why we simply use, we set like a 12-bit immediate in the I instruction so that we can take care of these immediate kind of instructions. Some other very important ones to know are the U instruction format, which is the long intermediates, which I believe is LUI and AUIPC. Then you have the jumps, or the unconditional jumps. I have another slide on that. I'll get more into it. Then we have the register instructions, which I covered earlier. Then we have the immediate instructions, which is almost any function that takes in an immediate. Not every function, but most functions that take in an immediate. And then we have S instructions, which are basically memory. So store byte, load byte, store word, load word, and so on and so on. And yeah, a big tip is to look at the green card to find the relevant opcode and func3 and func7 when trying to put together what an instruction is in binary. I know in the reference card this semester, they made it a lot easier to like figure out where these values are. So do make good use of it on an exam. And then yeah, translate registers to their numbers in 5-bit binary. You're not interested in the actual values, but simply the registers. And yeah, a cheat sheet tip is you can include how immediates are formed for each format. So for example, what I will talk about later is that jump instructions, the immediate is actually the offset in between like the instructions you're trying to go to. And however, I is simply just the immediate user specified formula. Okay. Yeah, and then O is the opcode, which is basically unique for a instruction format. Yeah. Okay, jump. Jump, there are two main, there are two instructions that you should know that have actually been defined for us in RISC-V, and there are two pseudo instructions that are also important to know. So there are two instructions for when there is a label provided, which are J and JAL. But the difference between J and JAL is that you want to use one of them if you do not return after you call your jump, or you want to return after your call, which is like when you want to link. And so that's what J is used for. J is used for not returning after your call. And that's what JAL is used for. JAL is used to return after your call. And then the same goes for the JR and JALer. So JR, basically, you will simply jump to the value address at that register, and you're not worried about where you come from. You just want to stay there. However, in JALer, you simply link the value, and as a result, you will make sure to, after you jump to the address at the register you're calling JALer on, you'll guarantee to go back. Any questions about jump? Okay. So normally the kinds of questions you'll get on a midterm involve not only like coming up with RISC-V code, but it can also include questions such as converting RISC-V instructions to binary or machine code. So I think I'm just gonna go over this really quick because I know that translating instructions to binary is a really tedious process. So for load word, if you go to the reference card, you know that the load word is an I type. And so if you go to the reference card, you will also find the opcode in func3, which is 000011, and the func3 is 010. And so you keep those values in mind. Then you have the RD, which is the 5-bit number, which is the 5 bits, of course, corresponded to the T5 register, which is X30. So it'd be 0B11110. And then you have RS1, which is T6. and that's x31, which is 0B111111. And then you have our immediate. Our immediate is 17, and you can tell by where the 17 is located that is the immediate. And then you can simply translate your 17 into binary, which is 000000010001. And then we can go ahead and put it all together. If we go to the instruction formats as seen here at the bottom, what you will find is that, okay, we put our opcode first, then we put our RD bits, then we put our func3 bits, then we put our R1 bits, and then we have our immediate. And all together, if we put that, and you put that back into like hex, then you will get the instruction 0x011FA F03. Are there any questions about this? Yeah, and a tip that I put is that to write out each part of your instruction to make it easier to find the instruction in binary. Oh, I forgot what I meant when I put that, but like as like what you can see here on the screen is that how they put I wrote out the opcode and then the func3 separately, so that you're not just like trying to scramble and then, oh, you find an opcode that looks right, but then you put in the wrong opcode. It's just keeping good track of the kind of bits that you're using when putting your instruction in binary. All right. Okay. Now, and then we have another kind of problem on an exam, which could be coming up with a very similar ISA, which can support a very limited amount of instructions but you want it to be as efficient as possible. So for example, we want on the spring 2019 midterm on question 5, it says, we would like to invent a new machine language based on RISC-V that uses fewer bits overall. To make this change possible, our reduced instruction set will only contain the following instructions: add, add-I, BEQ, and JAL. And additionally, we will group all of these immediate bits and place them together at the end of the instruction, so that basically our general format would look something like this: RS2, RS1, func3, opcode, and then im11 and 0. And then the instructions BEQ and JAL will encode the entire immediate necessary for control flow and do not append a trailing 0. But we still want to maintain support for all 32 registers. Okay, so let's say we decide to remove the func3 and func7 fields so that our R-type format looks like the following. We have our opcode, then we have our RD, RS1, RS2. How many bits do we need to represent each field? I'll let you guys take a minute to think about it, and then I'll pass. Okay, I think that might be enough time. Let's start off a little bit simpler. How many bits do we need to represent RD, RS1, and RS2 each? Yes, 5 bits, because we want to maintain support for 32 registers as mentioned earlier. And so we would need 5 bits for each RD, RS1, and RS2. What about opcode? Does anybody have an idea about that? Yes. Yes, it will be 2 bits. And the reason why it is 2 bits is because we only have 4 instructions we want to sort of decode in this new format. And as a result, if we want to make it as small and efficient as possible, all we would need is that our opcode to be 2 bits long. And so our answer here is that opcode 4 instructions still require 2 bits to enumerate. And then we have RD, RS1, RS2, still 32 registers. So as a result, 5 bits each. And yeah, another tip I put here is that pay attention to how many instructions you want to include in your new ISA. And yeah. Okay, now using the values in your previous answer and assuming all instructions must be the same total size, how many bits would we have for the immediate field in an I type instruction? And just as a refresher, we had a total of 17 bits in the format that we came up with in the previous part. Anybody can answer. I believe it is. Yes, it is 5 bits because our RS2 field is simply replaced with the immediate. And yeah, that would simply be 5 bits. Another way of thinking about it is that since we know we have a total of 17 bits, our opcode is 2, you subtract 2. Our RD is 5, you subtract 5. Our RS1 is 5, you subtract 5. You're left with 5. And yeah, as a result, it would be 5 bits long. Okay, because we only have 4 instructions, we can't represent all of our instruction types. Which types are missing from our language? Just S? Yeah, so yeah, it would be S and, no, S and U because we don't have any memory instructions we don't have any upper immediate instructions. Now D, true or false? 2 of our instruction formats have the exact same field ordering. Basically, like the format that we have earlier, that will be the same format for at least 2 instructions. Yes, that's right. So yeah, it would be true. Yeah. So yeah, as I mentioned earlier, S and U are incorrect because these types are not in the list of instructions. But it is true for part D because the I and B both contain an opcode, 2 registers, and an immediate. In the regular base 32-bit ISA, yeah, they're distinguished via some ordering of the RS1, RD, and RS2 bits, and then immediate. But because we want to stick to one format that we saw earlier, we can see that yeah, ADI, BEQ are the same. Yes. Okay, so overall, some general tips. To tackle coding problem, as I mentioned earlier, to tackle coding problems, think about the C pseudocode first. So think about how we can break apart certain statements into certain RISC-V instructions. Then pay attention to which kind of instruction you need. So for example, if you are saving or loading a character, then you would want to use save byte and load byte because it is a character. A character is 1 byte long. And as a result, you would need to use like store byte and load byte. And for integers, because those are 4 bytes long, we would use store word and load word. And some important cheat sheet notes are some like important pseudo instructions such as load address, load immediate, move, J, and JR. I now realize that in the new form of the reference card, they have a lot of these listed out for you. So if you want, so it may not be that necessary, but at least still having a good grasp of how to use some certain pseudo instructions. Any final questions about RISC-V? Yes.
Wait, what does load address do then?
A load address, it's basically a store. If you have an address of a label, it basically stores that into a register. It uses a combination of, I believe, AUIPC and ADI to do that for you. Any other questions? All right, yeah.
Okay,
Wow, okay, we're 21 minutes over time. But yeah, this last section is just some closing tips for studying, for anyone who's still around and for anyone who might be willing to watch through all of this. But yeah, these are just some generally compiled tips that I think I've picked up over the semester's teaching, and then also just from past TAs as well. So conceptual practice, there's a lot of people who aren't aware that like the discussions, some of them are recorded. So if you go on the website and you missed one or you have like trouble with a certain topic, the last sections are all recorded, and the worksheet walkthrough videos are also all linked to there. And then for homeworks, you can always come like to staff to ask office hours, because 2A was due on Wednesday. We anticipate office hours next week to be a little bit emptier on the project side. So if you have questions, feel free to drop by. There's almost always like online support anyways. So if you can't make it to SOTA, do come out. I would say in terms of coding, if you're online, if you're taking the exam online, you won't be given a compiler. So I wouldn't worry as much about like, is this exactly the right syntax that I'm using? Or getting the general idea there is more important, I think, because things are going to be hand graded anyways. And then I would say exams that are good, spring 20, spring 19, spring 18, and I guess now spring 21. I haven't updated this, I realize, in a while, but spring 21, fall 21 are good. Summer 20 exams are great as well, or summer 20 and summer 21 exams are great for if you want difficulty of like, those are two of the more difficult exams, I would say. Same with spring 21. And then if you want to do any just sort of like general review before anything else, the quests are good for Garcia semesters. His style of questions are really different. Non-Garcia semesters, it's typically TAs, exam TAs who write the questions. Garcia semesters, he really likes writing the questions. So the style is different, but it's good for practice. And if you're like looking for a way to study, because like not everyone has like all day to devote to studying, what I would recommend is like being here is a good first start. Like if you have questions about any of the subtopics, post on Piazza, post on the midterm review thread, and get those answered there. And then from here, you'll like be able to identify a little bit more of like which questions and topics you have more trouble with. And then when you're doing the practice exams, I would do the first one untimed and also without any like notes or anything like that, and identify where you're having issues and what kinds of issues you're having. And so that way you can try to hone in on those a little bit more. But yeah, I don't want to keep you guys for too much longer, so I'll just cut it off here. But yeah, huge thank you for the AIs for putting together things and presenting and being generally awesome and answering questions. And thank you for everyone who stuck around almost an hour after it's done. The recording will be posted. There will also be a feedback form posted on the same or linked on the same post. So if you had like, oh, I would have preferred more of this or less of that, drop it there. It's optionally anonymous. But yeah, thanks for coming. Good luck on the midterm next Thursday. Yeah.